Hello everyone, and welcome into your now live stream. Hi there. Hi the Siphon, hi the Greg, hi, welcome. And today I have some hot coffee with me. Yeah, we're back in the coffee stream because I am feeling good today. And I want to keep that going. I'm in a really good mood. No way, stream time, same time making VC. Yeah, what a coincidence, isn't it? Just, wow. Hi the Reblax. Oh wait, you asked me when is the stream going to be? Oh wait, hold on, I should answer probably, because you know, it's kind of mean of me not to answer. Hi there, Inadequate Dark. Hi there, Greg. Did I say Greg? I don't remember. I don't ever remember. Say hi to Greg on some of these streams, I just don't remember. Hi the Thara. Hi, welcome. The man, the myth, the legend. Hi. Okay, so here's the thing. I may or may not have finished like half. Why am I so big, by the way, on the OBS? There we go. Why am I so well? Obviously I'm big because I'm big, but you know, had me twice. I'm not complaining. You know what? Better twice than none. I'd say it's better twice than none at all. Hold on, I'm just making one more thing. Doing one more thing real quick. Why are you in a good mood today? I'm just in a good mood, you know. You know how it is sometimes. You're just in a good mood. And that's just basically what happens. Hi, the lemon. Something might have happened today, but you would need to give me some time for me to actually tell a story, because I don't know if I should mention it. It's a long story, basically. Also, I got an idea for a fun project. Well, not really got an idea, as much as I stole it from Timon, shamelessly. Which I think would be a fun video idea. Which, I mean, it's not really a secret. It was on Discord. I want to make a quantum chess, basically. Reblax, make it. I made the baddest discovery. Oh, what? Do tell. What is the baddest discovery? Spill. Oh, I guess I can't focus. What am I doing? There we go. That's what I'm doing. Okay. Why is Timon not on stream? I don't know where Timon is. Not doing their job, joining on stream always. It's in his contract. I know what Timon's doing. I agree, it's ridiculous. I'm just hi Joto, hi, welcome. Let me switch to live chat to make sure that I don't miss out on Lemon's discovery. Hold on, I need to focus. Give me a second. It's been, to be fair, I have been awake for a fair bit, so I may not be operating at peak efficiency exactly, so I would need to give me a sec. Okay, I think I got it. Alright, so today, of course, I have done a fair bit for the video. I have, among other things, fully scripted the video, and I have done a bunch of animations. I just realized the among other things wasn't actually required because it's kind of all I did. But that doesn't matter, because, geez, I can just feel myself being slow. And so today we should probably record it. 49,500 make it, yeah. And if I finish this video, that should push us over the 50,000. 49.5, yeah. So first, something I found out: the musical items are distributed under the Wedge product, meaning they can alternate stuff between K multifactors and K forms. I did not understand a single word that Lemon. I won't be fooling ya. I will not be fooling ya. I like when you separate the words, I get it, but when you combine them like that, there's a lot. You know what? I think Lemon. I'm gonna. Yeah, I think Lemon. With all respect, I think I'm gonna leave you in Reblax's capable hands. I'm just gonna move on to my silly chemistry in the background. This is not a good chat. No, I can you open my calendar. Yeah, good for you. Okay. So, I have fully finished the script for the video. It's 8 pages, which is, I would say, average. That's fair, MAKiT. MAKiT, when is the video about penis and CP coming? Penis, that maybe soon, you know, when I'll be talking about NMR spectroscopy or EPR spectroscopy, then I would also probably mention the penis and the CP. Actually, what's the difference? Am I right? Yeah. Okay, hold on. I need my sip of coffee, but it's really gosh dang hot. I've overdone it. I have absolutely... I can have cold milk. I'm a genius. Oh my goodness, I am just so clever. I'm incredible. I'm just so incredible. Okay, I'm so smart. Alright. Oh, coffee. My beloved. Without context, that sounds very questionable. Well, it's just the penis. Basic chemistry. Basic-ish, I would say. Hi, Tectonic Bites. Oh, that's a good name. That's Tectonic. I like that. It's a pun, and I'm all for fun. I'm all for puns. All right. All right. If I sound a bit weak, then I do apologize. As I mentioned, I'm in a good mood, but I am extremely tired. So, today we'll have to record. Also, we get Blender. Right, we need to render as we go. Render the Blender as we go. So, equilibrium constant, that's a bit further. Oh, the geometry nodes for this will be fun. So, right here, this is what we've rendered so far. And then right here, 600 to 630, and this, we just wanted to rotate negative 180. Yeah, fine, why not? As if I care at this point. Do you have Discord? Yes, I do have Discord. I have a whole server. Have you not seen any of my last segments of the videos? MAKiT's never weak. Exactly. Exactly. I shan't be weak. For I am never weak. That's a fate that only mortals must suffer. For I am mighty. Alright, so. so. It's good coffee. We need to record the video, which will be a bit of an odd thing to do on stream. It might be a bit confusing, but we can figure out. Okay, first let's do a microphone test, just to make sure that I'm recording with the right mic, and that is recording it all. Would you look at that, it is. Make sure that I'm recording with the right mic, and that is recording it all. Great, phenomenal, lovely, fantastic, festive. All right. me. Oh. Okay, so let's start simple. I've already covered the bare bones basics in the last video, so we'll just start where we left off. This is butane. If you take a look at its charge distribution, you can see that it's neither nucleophilic nor electrophilic. And so, oh wait, what's that? I've never covered what nucleophilic and electrophilic means. Oh well, that's any troubling. Okay, fine, I guess we're doing this. Alright, so believe it or not, we actually have to start with the 4 fundamental interactions. Why? Well, it's because using them you can describe every other interaction in existence. That's what fundamental interactions mean. Now, as it just so happens, this basically translates to describing everything. And because of how broad an interaction is in physics, and now, as it just so happens, this basically translates to describing everything, and because of how... Damn it. What's wrong with me? Making this legit amazing at this. What am I amazing at? What? Hold on, I got a compliment. I need to focus my entire attention on it. What am I amazing at? I agree, I'm great. I just want to make sure we're on the same page. Algebrain rotted. that's a really good term. I from serious. I'm not getting it, Jota. I'm just not. I'm you get algebra rotted. You can read the thing and act the thing without thinking. I mean, yeah, acting.
Okay, so
Jeez, that's loud. Shut up, MAKiT. No one cares. There we go.
this is butane. If you take a look at its charge distribution, you can see that it's neither nucleophilic nor electrophilic. And so, oh wait, what's that? I've never covered what... Okay, fine, I guess we're doing this. Alright, so believe it or not, we actually have to start with the 4 fundamental interactions. Why? Well, it's because using them you can describe every other interaction in existence. That's what fundamental interactions mean.
Okay, right here.
That's what fundamental interactions mean.
Now, as it just so happens, this basically translates to describing everything because of how broad an interaction is in physics. And as it just so happens, chemistry is a subset of everything. So, how do these interactions affect reactions? Well, strong is responsible for forming of hadrons and atoms, but it disappears too quickly to affect reactions. Gravity has the opposite problem. It would need much more massive things than molecules to affect them. Electromagnetism, however, fits in perfect. It absolutely pops at molecular scales, and that's why it is the interaction behind the reaction. Oh, don't mind that, we don't talk about weak interaction. That's a long story for another time. But yeah. But this basically explains why chemists are so obsessed with charge. So first we have a proton and an electron. Proton is positive, electron is negative. Opposites attract. Simple. So the first term that chemists use is positive and negative for precisely that reason. Usually individual atoms have an equal amount of protons and electrons, but they don't have to. And then they become ions. So right here we end up with more fun words to add to our vocabulary. The cation and the anion. Cation is basically a positive atom, and anion is negative. I guess it could be also molecule. Wait, am I wrong, or can't just ions also be molecules? Why so serious? It's pretty fun. Good one. Greg, come on. All right. Will I finish off?
An anion is negative. Okay.
Yeah, my memory is a bit shaky at the moment.
An anion is negative.
Then we have the power of hydrogen. So how many hydrogen ions are in our solution? The scale is logarithmic, which means it can't spiral off to infinity, and it's confined between a 0 and a 14. Now, positive hydrogen ions are just positive charge. So it's basically a measure of how positive or negative our solution is, with a couple of asterisks I'm not gonna get into. This scale is called the acidity, because it basically tells you how acidic something is. The more positive, the lower the number, the more acidic. Oh, oops, yeah, I forgot to mention, we also multiplied the logarithm by a minus, because chemists just love it when things aren't confusing and are actually simple. Now acids want to lower their charge, so Lewis acids get more negative. Lowry acids get less positive. And that's just 2 more additional words to chuck in there, you know, just to really get you to memorize all of them. So there, we already have 3 separate terms, but watch out, here comes another tool, electrophilic and nucleophilic. Philic is the opposite of phobic, so philic basically means just loving. In this case, loving electrons means positive-ish, and nucleophilic means negative-ish. So there we go, 2 more terms, but wait, there is more, because there is also the electronegativity, which is basically how much something attracts electrons. Wait, MAKiT, isn't that just positive charge? Well, it can be, but it's more about like electrons having less energy when it's there, which, I mean, just watch my previous chemistry videos to learn how electrons can have lower energy due to quantum mechanics bullshit. Okay, that's enough for now. Ballast proof for Gen Stokes. That is a wild journey to get to Stokes, I do have to say. Oh, why am I not so not comfortable? There we go.
Electrons can have lower energy due to...
You need a PhD in everything in math to even stand any proof. I wouldn't say that, Greg. I wouldn't say so. Because the thing is, for proofs, decoding proofs is difficult, understanding them is not. Like, the most difficult part of a proof is creating. Once it's actually created, it's usually trivial to explain. The only problem is that mathematicians are really often bad at explaining them, I would say. That's in my opinion. In my opinion, most of the time, the proofs themselves aren't difficult. It's that really often mathematicians are just bad at explaining what they've just done.
Mechanics bullshit. Okay.
So as a quick recap, we have negativity, positivity, negative atoms, positive atoms, negativity measured by the negative amount of positivity, positivity measured by the negative amount of positivity. Damn it. Okay, again. So as a quick recap, we have negativity, positivity, negative atoms, positive atoms, negativity measured by the negative of the amount of positivity, positivity measured by the negative of the amount of negativity, of negative positivity. Damn it. So as a quick recap, we have negativity, positivity, negative atoms, positive atoms, negativity measured by the negative of the amount of positivity, positivity measured by the negative of the positivity, and negativity because it's the negative for the positive, positivity because it's positive for the negative, and my absolute favorite, negativity as in positivity for the negativity of the negativity, keeping in mind that the first negativity refers to negativity, whilst the second thing refers to the positive-negative relation of negativity and positivity in not charge terms, only mathematical sense. Now, all of these words refer to this charge in different scenarios, but they all just translate to either charge or the way it influences charge. And yes, there are more. I could also mention oxidation, reduction, and it just keeps going, but the one we'd like to focus on is this one, electronegativity, which we'll use like this. No, proofs are not trivial to explain, unless by explain you mean give a very vague idea. No, because even if you go in really strict, they most of the time, unless, I don't know, maybe I'm just looking at weird proofs. Supersonic speed, might become a rapper. Proofs are not trivial to create, but once they're actually... Okay, what kind of proofs are you talking about, Reblax? Because I am biased in this case with like proofs. No, hold on. Give me a sec. As I mentioned, I'm tired. Give me a sec. A while back ago, I went through this thing. What video was I going for? I went through, I think it was an MIT paper. I remember it was painful. Was an MIT paper Was it for the Fourier? It might have been for the Fourier, but I don't remember exactly. Long proofs of set interiors. Yeah, I mean, those proofs can be long, but they're not actually... Once you decode them, there's nothing really difficult. Because the thing about mathematics, what makes it different than stuff like physics and so on, is that in mathematics, you don't really need all that... You don't really need this much assumed knowledge. You always need prerequisites. Yeah, but you don't need... So, for example, when you're dealing with a certain kind of assumed knowledge, I mean, like, when you're reading a physics proof, right, then you are starting with the experiment, and then you have a model trying to fit that experiment. And because of that, if you haven't actually created that model, then it's really weird to try to understand the model. It's because it really often it just assumes a bunch of stuff which are like only the inventor gets why it's there. But in mathematics, it's not really that. In mathematics, there is a logical reason, a very like logical to the core reason for why things happen. Hi there, Christopher Columbus. Hi. So even when proofs are long, they might be long, but it's logical to the extreme. It's similar to Kelly Hamilton. You need to be comfortable with the character's polynomial. So with determinant and evaluation of polynomial at endo. That's a lot of words. If I don't know if I was supposed to, because I didn't. I'll be honest. It's just like it's just like when Lemon started this. I don't understand what that means. Rushing, but that approach is not satisfactory since you need to provide the reason. C is a lot of words. Yeah, but Reblax, just because stuff is a lot of words doesn't mean it's difficult. Like, when you look up equilibrium constant, you define as the equilibrium constant of a chemical reaction is the value of its reaction quotient at chemical equilibrium, a state approached by a dynamic chemical system after sufficient time has elapsed at which its composition has no measurable tendency towards further change. For a given set of reaction conditions, the equilibrium constant is independent of the initial analytical concentrations of the reactant and product species in the mixture. Thus, given the initial composition of a system, known equilibrium constant values can be used to determine the composition of the systems at equilibrium. However, reaction parameters like temperature, solvent, and ionic strength may all influence the value of equilibrium constant. Like, equilibrium constant is trivially simple, but when you put it this way, it doesn't look like that. It's not difficult, but it takes time to properly understand. Well, I mean, obviously long proofs will take a long time to understand them. They're long. You can't really shorten down the proof. What's the prerequisite for counting? Bye, Greg. Bye. See ya. Wait, I got it right, correct, right here.
So as a quick recap, we have negativity, positivity, negative atoms, positive atoms, negativity measured by the negative of the amount of positivity, positivity measured by the negative of the positivity, and negativity because it's the negative for the positive, positivity because it's positive for the negative, and my absolute favorite, negativity as in positivity for the negativity of the negativity, keeping in mind that the first negativity refers to negativity, whilst the second one refers to the positive negative relation of negativity and positivity in not charge terms, only mathematical sense.
Jesus, incomprehensible. I love it.
We'll use like this.
And then right here we have piss off. There we are. Equilibrium constant is really not trivial though, is it? It actually really is. Reblax, here's the thing. Like, when you have a reaction, when you start with, let's say, burning hydrogen and oxygen gas, right? You have your hydrogen and oxygen gas. When you finish your reaction, then you're going to have a certain amount of hydrogen oxygen gas, and you're going to have a certain amount of water. The ratio between these two, that's the equilibrium constant. That's it. That's it. That's all the equilibrium constant is. Like, There is not much else to it. It is so trivial. Especially when you compare it to like actual thermodynamical chemistry, which is painful. The intuition says you would have a way to measure how advanced the reaction is. This isn't really, no, it's not even how advanced the reaction is, just this is what happens when the reaction is finished. How the fuck do you like figure out the formula? If okay, I'm gonna do it completely from memory, but if I'm not mistaken, then the equilibrium constant is equal to E to the delta G divided by T and something. I think that's it. I think divided by T and something. Hold on, let me check. I'm gonna check on LibreText and we'll see how close I was. If I was in any way close, I'll be impressed with myself. Of organic reactions. Where do drugs come from? I think it's this one, right? I've explained in the video and I missed it. Yes, well, I have explained it, but I didn't mention it was Gibbs free energy. E to the negative delta GT. Damn it, I was so close. Oh, if only I've added the negative, it would have been so perfect. Basically, delta G is the difference in bond energies. That's basically what it is. So, you know, if hydrogen and oxygen gas, so I did explain it, but I didn't mention it was Gibbs free energy. If hydrogen and oxygen gas has a certain like G, and if water, which is what you then get, if water has a smaller G, so the bonds are weaker, right here, let's call it G1 and G2, then delta G is just G1 minus G2, if I remember correctly. That's it. That's basically the difference in bond strength. You could break it down even further, like you have this, delta G equal delta H minus TS, but that's, yeah, I mean if you want to, but delta H is just the bond energy actually, and this is, I think, it's just entropy. If I'm not mistaken. So it's not trivial, it's just poorly explained. The thing is, Roblox, in this video, I'm gonna explain it really well. Yeah, in this video, actually, I'm about to enter the chapter where I explain it. Where this is, yeah, I'm working on the animation for it, and you can see me explaining precisely that. But the next sequence of animations will be me explaining it more in depth, and you'll see just how obvious it is, the equilibrium constant. But I don't blame you for thinking it's not trivial, because it's so poorly explained, always just so poorly explained. What's up with the units of the ideal gas constant? Let me see. Ideal gas constant. What would be the units? That's a lot of them. Yeah, my goodness. They really wanted to cover all their bases. Wasn't the film I was given as cool though? I was just told the thing was stoichiometric numbers and stuff and liquids and solids don't show up because reasons. Yeah, but that's precisely my point, Reblox. The thing is, I dislike it so much when complex words are used in places where people where people use them to learn casually. Complex words should be left for the scientists for the people who are advanced in a topic. That's what complex words should be used for, because yes, complex words and expert vocabulary basically is useful for the experts because it makes things easier. Lemon doesn't have to explain what musical isomer is every single time. Lemon can just say musical isomer and just cut out the middleman. But in places that are not supposed to be for the experts, like Wikipedia, that's a crime to explain the equilibrium constant this way. My people don't want to tell people for that. Drug proof stuff. I mean, yeah, you do need to prove stuff. What does it? I just don't quite get what your point is there, Reblax. Because all I said is that when I don't know who said, I don't remember. It was C# minor or was it Greg? Where basically he has 11 thumbnails with balls in a row. What can I say? But you know, when someone said that you need a PhD to understand proofs, that's what I disagree with. Because you don't. I mean, first of all, you don't need a PhD to do anything, but if we're talking about like PhD level knowledge, then to me, you do need that to make proofs, to actually create new proofs. You would need that because that's a tough thing to do. But actually understanding them, I don't think so. To me, that seems much like the much easier problem. Okay. Is vector space the same as linear space? What is linear space? Someone who can't given the independent proof, but they don't know how to build, so they can't get the actual proof. How do you mean? Because they can't get an actual proof. You mean like when someone reads the proof without understanding it? Is that what you mean? Oh, I need a drink. I can't do this sober. Linear space. Linear space. If it's the same as a vector space, I don't like that then. The linear space. No, actually my space is logarithmic. Hey MAKiT, what part of calculus do you use every day and the part of math you never use, like ever? When it comes to calculus, Ty, can I come to the stream to discuss briefly? Reblax, you can always come on the stream. What do you mean? You don't need to ask permission. You have the access to the channel for that reason. Have you not been joining streams because you feel like you need my permission? Any day you want to, just join in. But let me answer Soba's cables thing. MAKiT, what part of calculus do you use every day and part of math you never use? When it comes to calculus that I use every day, because I did mention I use it every day, is simply because I just find it easy to think in terms of functions. Like when you approximate stuff, wow, it was loud. Hi, Roblox. When you approximate stuff with functions, it's much easier to create different shapes, and it's much easier to manipulate those functions with calculus than with just like general subtracting the x and whatnot. And when it comes to part of math I never use, that's knot theory, simply because I make fun of it so much that I can't even learn at this point. I can't. My commitment is too great to making fun of knot theory. Hi there, Reblax.
Hi guys, Reblax here.
Jeez, you are full volume. Oh my ears. Hi.
I'm sorry.
No, it's fine. It's fine. I turned you down now. It's fine.
Alright. No, I asked to come on stream because like we're recording and stuff, and I assume you don't want my voice for that.
No, it's fine.
Hi, Pharma Main.
Why did you
Good to
let
see
the
you too.
French in? This isn't actually the first stream on which Reblox is. We already had it.
It's like the third.
Yeah, I mean,
stream
you've
I
joined
came
in on stream before the elementary particles video because I remember
Yeah.
that's what I needed league or groups for, not even league groups. I still don't know how league groups are. I needed just groups. That's what behind it was.
Yeah. Now, basically, the thing I was saying is that you can take a lot of details out of proofs, and that's actually how we math people remember them, I think. At least that's how I do it. Like when I remember, like there's a lot of proofs of stuff that I just don't need to remember because I can just like treat them as simple math problems, and the important thing is not really know how to do it because it's usually easy stuff and it's just brought up in class, so you know it's true and you can use it to do math with. But if you need to reprove it, it's usually fine. And for big theorems, what you do is you just memorize some kind of big ideas in the proof, big ideas. And then if you need to ever write out a real proof, a cool proof, a formal proof, a rigorous proof, well, then you can fill in the gaps, but that requires a math background.
Oh, but
And
I meant
so
for understanding
I
proofs.
I can explain the proof of like the Cayley-Hamilton theorem in a simple way, but it won't really provide a proof to people that don't have the necessary math background to fill the details in.
No,
But for instance, in math seminars, in research seminars, when people talk about like big ideas and stuff, like we don't do like formal math in math seminars because it's not the point. It wouldn't be that useful. You can't really expect someone to follow everything you say, so we just talk about big ideas mostly, and that's fine because it's the point. But you know, the actual math needs to get done at one point.
I mean, yeah, what I meant is I specifically meant for understanding proofs. That's because, like, every single. What I really like about math is that there is no such thing as the proof of something. So when you have, I think there are at least four. There must be more, but there are like at least four different proofs of the Euler's formula, and there is no actual.
That sounds about right.
Yeah, there's a lot of them, and the thing is, there is no actual the proof of Euler's formula, and that's simply because if something is equal to, then you can take a lot of different paths to get there. And what I basically meant is that when you have these mathematical proofs, then every single operation and every single action, even more general, every single action in mathematics has like an interpretation for it. No matter, some of them are incredibly complex and convoluted, and it takes you days to get to the actual interpretation, but every single one of them has, simply because the underlying tools have an interpretation. And so when you have a proof of something, you can get deep enough to get the interpretation of that proof, in which case you will just understand it. So I don't mean like simplifying a proof to memorize it. I mean understanding what something does, like understanding why it works. So, for example, for the the reason why the derivative of e to the x is itself, like there's a lot of different ways you can approach that to understand why that is even a possibility, without the need to there's a lot of ways you can. I'm sorry, I'm really tired. This is taking a lot of mental effort from me. There's a lot of ways to approach that so that you understand why it works without the need to actually be like a professional mathematician. So, for example, you could go with derivatives of a c to the x at the different c's, and you can see that they follow a path that there is like you multiply by a logarithm. Well, natural log, but let's just assume you don't know it's a natural log. You can still assume that if the function is continuous, then it has to pass 1 at some point. And obviously you would need to prove that it's continuous, so on. You would need to prove all that. But my point is that there are a lot of ways to approach it so that you can understand what the function means. I just don't want people to have the false impression that when it comes to mathematics, that you need to memorize equations or something, or like, because that's a common misconception people have about mathematics is that when a mathematician sees like an incredibly complex equations, they think of them in a purely abstract form, which, I mean, I don't know, maybe, I don't know if you do that, maybe there are some mathematicians out. I wouldn't even be surprised if you do that, honestly. At this point I would just accept, but from a lot of people who do mathematics I've met, I haven't really seen that. That's really not the norm, where if you see a really complex equation, you think about it in terms of the equation, not the... Am I making any sense?
I'm not quite sure what you mean by
Am I making any sense?
equation
I'm not quite
abstractly.
sure. Basically, how when you think of... Okay, when you think of groups, right?
Yeah.
You don't really think of them as the operations you can do with groups, only you think of them as like, I'm lacking the mathematical vocabulary to express myself, but basically set of operations. Would that be fine enough? A set of operations?
Honestly, groups may be a kind of accidentally bad example because I read like slides of for a presentation that were done by the former professor of logic of my uni, and in these slides he says something. He's like, basically that you've got a real lot of people who do technically stuff with groups, but it's because the definition of a group is so large that you can really just say something interesting about all groups. Really interesting theorems come when you restrict yourself to certain families of groups that correspond to certain situations in math. And I guess the way you think about what a group is or does really depends on what kind of group you're considering.
Yeah, but
So, for instance, if you're doing finite group theory, when the groups are finite, we can say interesting stuff, and that's a miracle. If you're doing finite group theory, well, it depends on where your group comes from, basically. If you're like doing pure group theory, your group is just a group, so you're thinking that it's purely algebraic object abstract thing. Maybe you were going to try and make it sell pun right there. That's your pun for this stream. I hope you're happy with it, chat. You're going to make it act on certain finite sets to study it better. But for instance, if your group comes from geometry, which happens like a lot, so for instance, Lie groups are symmetries of stuff, or rotations of a cube, the examples I gave. If your group comes from geometry, well, maybe you're always going to keep that in the back of your mind if what interests you really is the geometry.
I'm an idiot because I just realized
the natural
much
questions
better.
to ask are, when you say something about the group, what does it say about the geometry? Because that's the interesting part. That's why we study the group.
Yes, okay. You just gave me, I think, the perfect example of what I'm basically trying to... Because the thing is, I could have gone with functions, but I feel like functions would be too specific. I want to do something general. A perfect example of what I'm basically trying to say is, you know, like abstract spaces, right?
Yeah.
Like, even the term itself comes from abstract space.
It's very funny because abstract space is not actually a math term. I guess the notion you'd be looking for would be topological spaces, but when people do really abstract geometry, they tend to just say abstract space to not scare off the classical geometers in the audience.
Maybe, I mean, to be fair, that's the problem. I'm not a mathematician, right? I haven't gotten to the actual extreme math stuff, but
well, you'll get there eventually.
No, because
it's coming for you. Don't
listen,
worry about
that's terrifying. The way you describe it, it's terrifying. It's a curse. But okay, then I suppose that's the flaw. But okay, I'll be honest. I'll be real. When it comes to abstract spaces, the way I've heard that term, I think the place where I've seen it most is like abstract space of possibilities, which is basically when you just have a lot of variables, and so for example 7 different variables, and you want to describe a certain... Well, that's exactly the thing, because the way I always thought of it is when you have 7 different variables and you want to restrict those variables in a certain way, you just imagine it as like 7th dimensional space where you just take a certain volume of that space, and that's your
Yeah.
like space of possibilities. So, for example, this is precisely what I mean. So when so for example, if you have a drone, did I open the second paint? I'm just too greedy. I'll just reuse the one. So if you have a drone, a flying drone, I think I got that from Robert Miles, if I'm not mistaken. But if you have a flying drone, and this drone exists in just our world, 3D space, then in order for it to avoid flying into some certain trees, you would restrict its minimum height to a certain value. And in order to for it to avoid flying into planes, that's not close enough. In order for it to avoid flying into planes, you would restrict its maximum height to a certain value. Then, in order for you to avoid it flying into buildings, you would restrict its distance also to a certain value, and you would basically enclose it in this sort of three-dimensional shape where it can exist.
Yeah.
So in this case, you are literally restricting it to a space. But restricting stuff to abstract spaces, how I is when, because to be fair, as I mentioned, it's not, I didn't learn that from maths. I just learned that from like maths being applied in different fields. Is when you have something like an AI on the stock market, for example, dealing with the stock market. Like, you don't want it to do certain kind of investments, but the stock market isn't three-dimensional. It would be a lot more dimensions because there will be a lot more different variables. And in that case, you are restricting it in the abstract space. Or for example, with a car, you not only want to restrict its three-dimensional position, but you also want to restrict its maximum acceleration and deceleration to not kill people on the inside. Like, you get what I'm saying in this case.
Yeah.
And what I basically mean is that if you had this sort of self-driving car, if you wanted to describe all the ways in which you're restricting this abstract space, it would be a terrifying equation. Because you would probably restrict it differently for the physical space, you would restrict it differently for the acceleration, deceleration, you would restrict it differently for the usage of different road signs, so on and so forth. And so it would be a terrifying, massive equation, but when a person that uses that equation looks at it, they don't really think of it as these separate characters, all these integrals, all these functions, only they think of it as that abstract, let's say 20-dimensional space of possibilities. And so maybe I'm wrong here. That's I'm not a mathematician. You're the mathematician in this case. So if you're gonna tell me that's not how it works, I will accept that, because I mean, yeah, I do believe you have more experience here than me. But that's how I always seen it. So when you have what would be a good one? I want a pi function. Is pi function the one I'm thinking of?
What do you mean by pi function? Like the prime counting function?
The prime count, yes, the prime one.
Yeah.
Okay.
Obviously, this one. The one.
Yeah. So the pi function, like when you look at it, you don't think of it as just the function pi. You think of it as the prime counting function. You think of it as the meaning behind the function. So when you see, when you see the pi function,
I think I get what you're saying. Yeah.
Yeah, that's what I mean.
We try to think. I mean, I guess. Fool! It's time for philosophy. We're Platonists. Most mathematicians, I think, are Platonists.
Oh no.
If a philosopher asks us, we're probably going to answer and say, oh, no, math is about like abstract manipulation of symbols and they don't mean anything, we will leave us alone. But secretly, behind the scenes, I'm telling the truth about like the big secret truth that big math has been hiding from me. Secretly, we actually believe that stuff exists.
No way!
We actually believe in like the real line and stuff.
That's the insider secret with Roblox right now.
Personally, recently, I started attributing believability score to every math object I know. So vector spaces have a believability of 1 because I'm kind of sure they exist. Modules are 0.99 because how the fuck is a submodule of a free module 3? Infinity categories are probably like a 0.2, and when I learn them, they'll probably be like a 1, and I probably will never shut up about them, and so on and so forth. but yeah, we tend to think about the meaning behind the objects because, well,
I mean, that's
if
how
at
they are
some
created,
points,
basically.
yeah, it's how they are created.
You can't recreate something
And I
new
mean,
without giving it a meaning because I mean, then you won't
technically,
create anything new. You're just gonna create new notation, basically, for the same thing.
technically, I'm quite sure there are. It doesn't really happen like in my classes because I mean I'm not doing like research level stuff. But for instance, if I'm not mistaken, so I'm not really a number theorist, even though I have like 2 number theory books, but I haven't read them because I'm afraid. I'm not a number theorist, but I know that like there's this big theorem in algebraic number theory that's called the quadratic reciprocity law, which it relates squares in interesting number systems basically, and I think I'm overhyping it. It's actually not that hard to understand, but the proof was found by Gauss. Obviously, it's Gauss.
A
But
ghost?
actually, when you and actually, I saw a proof like or my algebra one. That's my group theory course. Actually, not what US people think of when they hear algebra one. Uh, my algebra one teacher is actually a number theorist. Like he does research in number theory for a living. So obviously, he
I
showed
think
us some
I
good number
remember you
theory
mentioning that
stuff
actually,
in our
if I'm
class.
not mistaken. I think at one point.
What?
I think you mentioned that actually at one point about your teacher being.
Yeah, I probably
And
did.
I remember,
When
yeah.
explain groups. And yeah, so I mean, and like yeah, he talked to us about like it was a part that was like really basically introduced a lot of ideas, and you can absolutely understand every step of the proof. But if you ask how the fuck did anyone think of this, the answer you're met with
Weed.
is it was Ghost. and actually, that's not to say that you can't find interpretation behind the stuff. I
But I
talked to
mean,
like some
that's
guy
actually
who's
the
more
whole
advanced than me.
beauty of math, isn't it? That when you that's what I said.
Yeah.
Understanding the proof isn't that bad. Coming up with it is mad. And it actually
Yeah.
because the thing is when you take things separately, like for example, Euler's formula is so mind-numbingly obvious the more you learn about it. Like it's just it clicks. It makes so much sense. It's so obvious.
Yeah.
But if you lived in a world without the Euler's formula, actually coming up with it, like you would need
Yeah.
the amount of weed.
You're reinventing the famous physicist jokes, which say that mathematicians only prove trivial theorems because once a theorem is proved, it's trivial. It's fucking obvious. How can you be so blind? But basically, like the thing is that in the proof of quadratic reciprocity that we saw, we needed to introduce certain sums, and like we just introduced them from nowhere, and whoosh, it works. And some guy that's more advanced than me, he doesn't do number theories actually into differential geometry. But he told me that you could like actually get an intuition for why these sums specifically work and where they come from if you do p-adic stuff.
Oh, that's the.
I haven't done p-adic numbers yet, so I mean I know what they are, but I haven't really like.
Isn't that, by the way, just because I only very briefly looked in them? Isn't that just describing any number in relation to a certain prime to the nth power, like an infinite sum of that prime to the nth power multiplied by something? I remember. I mean, all I remember is that there was like the infinite series.
So p-adics were invented to like apply power series techniques to number theory by some guy named Kurt Hansel. I haven't looked into the details, so I couldn't really explain it. And maybe I should actually. It looks very interesting. I'll do that later. But basically, you have multiple ways of constructing the p-adics. So, for instance, when you try to construct the real numbers, you can start from the rationals and fill in some holes, in a way. But the holes depends on how you think of the topology of the rational numbers, the shape. And if you change how you think about the shape, you get different holes. And when you fill in those holes, you get the p-adics. So that sounds very vague.
So that sounds too.
And that sounds very unrelated to power series, also.
It's on. I mean, honestly, It sounds like something a mathematician would say.
Yeah. Now, the really cool thing about this approach is
Did
that
you just?
basically the p-adics are actually not that weird.
I
Like when you
maybe
try to fill in holes in the rationals, you either get the reals or some p-adic field. So in a way, they're natural objects to think about in a way, and that seems pretty cool. Like when you fill in the holes in the rationals, you either get the reals or the p-adics, and no other thing can pop up. Like I think that's pretty cool. This is one of my favorite theorems, actually. I have a lot of favorite theorems. Now, maybe the easier way to like think about them is that you can kind of think is the when you try to write like 99999 repeating, but on the left side, and you notice that when you add one and you carry over every time, and if you do it an infinite number of times, you get 0. Well, you can actually make this idea precise using some algebra and powers of, well, for p-adics, you're doing that in base p, so powers of numbers. And that gives you not all the p-adics, that give you the p-adic integers, and then you can basically just do fractions with them and you get the p-adic analog of the rationals. Well, the p-adic analog of the real line, really. So
wait,
yeah,
so when
that's the easier approach.
When it comes to p-adics, is it? I feel like I'm a 6-year-old and like an adult is trying to explain to me how to drive a car or something. Because I mean,
what do you mean you don't understand? It's just like the
correct me if I'm wrong. Didn't you say
projective or inductive limit or on something?
The thing is, when you bring topology into it, like
there's no real need for topology. There's just like
but even
my favorite theorem.
Even if you
can do it purely algebraically.
I mean, even if there's no need, I'm not a mathematician enough to link something like p-adic numbers to topology. I know it's possible. Where there's a wizard, there is a way. Describe everything with knot theory, but
no, but like the easier. I mean, you can explain it to. Basically, you can kind of. The intuition would be like infinite digits in base p, but infinite digits on the left side instead of the right side. So, and from there you can kind of make it formal, and I could probably explain that if I actually knew which way the arrows go, which I forget every time because I'm bad at stuff. Which way do they go actually? And actually, like, you can draw a neat diagram, and then you can figure out that p-adic numbers are really just. You need some modular arithmetic. Familiarity with modular arithmetic would make this much easier to explain. But it's not that scary. Modular arithmetic is just like.
The arrows go up unless they go down.
They go sideways. Basically, everyone in like algebra is using an arrow-based notation for limits and co-limits, and me, an intellectual, memorized what's a limit and what's a co-limit, but can't figure out if the arrows go right or left every time. Yeah, but basically you can kind of, actually, I'm getting angry. I need to look up if it's like limits or co-limits.
One thing which is really annoying me in math, I know that's completely unrelated to what you're saying, I'm so sorry for that, but one thing which is I really dislike it, is when people say log x to represent the natural log. It's awful.
We don't do that in France, we use ln.
Yeah, because ln is the proper one. Log x.
I know that people in number theory really, I mean, in the US, I know they just write log and they don't think about it.
That's awful. That's awful. That is so awful.
It kind of is.
It really is.
Yeah, notations are. I mean, if you're trying to get mathematicians to fight, you can probably like make them start talking about notations.
I don't know. No, notations in maths is. I feel like it's the most tame notation wise, because the thing is, every single branch fights over notations. In chemistry, we had the fight over benzene. Which way should you draw benzene? in physics, what would there be in physics? I'm saying there's something
Chemistry.
in physics. There's a lot, but in mathematics this is the most tame, because if something is just a matter of notation, then no matter what notation you use, it'll still at least like mean the same thing. Not only be the same thing, but mean the same thing.
Yeah.
But then in other ones, it's even worse than. I mean, okay, still using a log. Oh, this
I mean,
article
like,
uses technical mathematical notation.
The way you need to think of notation is that you need to remember that your brain is, well, human brains tends to be bad at math, and notation is a neat little helper to help you make the math a little easier to.
Yeah, language is basically vague. That's the issue. It's the same reason why programming languages exist. Like,
Yeah.
like technically, you could do all maths without any notation. You could just do them by writing down words, but then eventually you will have a bunch of people say stuff that could mean different things, and then ambiguity kicks in, and then all of a sudden you don't know if this proof is you can apply it to a certain scenario or you can't because it's vague. That's a nice thing. Then basically, congrats, you created philosophy, and if it's vague and no one wins.
Yeah. All right. So it's an inverse limit. Because people say limit, co-limit, projective limit, inductive limit, direct limit, and inverse limit. And direct limit is actually co-limit, because co-limits show up way more.
I didn't even know there was many limits.
And also they have absolutely nothing to do with the limits in like calculus and analysis.
Oh, I see. Of course.
It's algebra all the way down. Yeah. No, actually, like p-adic numbers when constructed algebraically are like they're quite explainable for something so advanced. They're quite explainable.
I really am so bad with stuff like topology, for example. The closer something is to calculus, the more confident I feel. The further away it goes from calculus.
When I say topology, it's not even the like cool
no, I mean,
where mag is a donut and stuff.
I know what it is.
Topological spaces, so it's the hard part.
Yeah, I know what it is. I know, like, it's basically, once again, the difference between the baby mode, oh, it's understandable, versus the actual Chad math level of, oh, let's abstract it out of existence.
Yeah, there's also like, there's this problem, which is like, for instance, like one of the most important concepts in topology is compactness. And like, when you first encounter compactness, you don't call it compactness. It's when you're first year and you're doing real analysis, and you actually just encounter some theorem, the Bolzano-Weierstrass theorem, which is easy to state. And it's actually like, it's a very non-trivial theorem. Like, it doesn't sound true the first time you hear it, but it actually is. And you use it to prove a lot of properties about continuous functions, for instance. And it works, but you really don't feel like you could have, I mean, at least I don't feel I would have come up with it. And compactness is this, but like abstracted away beyond abstraction. And so you see a definition and you use it. So like now I'm comfortable with it. So I know when to use it. I know when I'm like, oh yeah, a compactness argument will work here and stuff. But like I couldn't have come up with compactness, and that's because no one has come up with that definition. The guy that came up with this definition came up with it based on the previous one we used, and we don't use because it's deprecated. Math happens with small improvements, but since we like need to teach stuff to undergrads and like people, and we can't really give you we can't really make you ingest like the whole 300 years of math history and whatnot. We give you the abridged version where we leave out the details. But it's important to remember that like people not only spend their lives researching and defining stuff, but also they don't start from nothing like you do when you encounter the things.
Once again, that's the most annoying thing, when just how obvious everything is in retrospect. It's so hilariously obvious, and it's so impossible to realize. It's I know it's not much. I really, The thing is, maths used to be the thing I was the best at out of physics and chemistry, but recently I've gotten so much better at physics and chemistry that it's no longer is. I've never been great at maths. I've been alright. And right now, because of that, whenever I try to bring up an example of something mathematical, I used to go to quantum mechanics. I don't know why. Just can't escape it. Actually, I'm curious because Lemon's been talking a lot about musical isomorphisms, right?
Yeah.
Like, the thing is, when I break this down, I understand what these words mean separately.
All right, so
they are
first up,
I-
music. You can ditch out the musical part. It's just that we use the
Yeah,
funny
that's
symbols
just-
because funny symbols are funny.
That's just funny because sharp is the inverse of flat, if I remember correctly.
And no, and actually, like maybe there's actually, if there's an actual reason for this and I don't know it, I will be so mad because it would be so funny to have an actual reason for these names. Actually, is Lemon still in the chat? I don't know. They didn't.
That's the curse. That's the case. So I'm probably when we mention musical isomorphism, you'll see Lemon will join in any second.
The curse.
Yeah, the curse of the.
All right, so musical. So.
Okay. Okay.
Musical isomorphisms are actually. Okay, so basically, you've got linear algebra, right?
Yeah.
Linear algebra. I won't say it's easy because you should never say that something is easy because the first time you encounter it, stuff is not easy, but the second time it's fucking trivial. But like linear algebra, yeah, we understand it like pretty good. Stuff works out very great. Vector space, finite dimensional vector spaces, very nice, very rigid, lots of theorems, lots of properties, everything works out very nicely. What's differential geometry? Differential geometry is when you add in geometry to the mix by basically kind of gluing vector spaces together. It's not really that. But basically, since in differential geometry you study smooth shapes, you can zoom in on them. If you zoom in on the surface of a sphere or of a torus, if you pick a point and you look very, very close, it looks like linear algebra. It looks like a plane. It looks like a space.
I remember that from the groups and the algebra. I remember that precise.
It looks like basically the differential objects in differential objects. The geometric objects in differential geometry, when you zoom in on them, they look like linear algebra. And actually, like, we can do linear algebra, and it's important. And musical isomorphisms are basically an isomorphism from linear algebra, which is that when you have a finite dimensional vector space, it's isomorphic to its dual vector space. And you try to do this, but on a geometric object. And it's slightly harder because since you're doing geometry and you want like you can just pick every point and say, well, I'm going to pick this isomorphism there and this isomorphism here and this isomorphism there. You can just define a function point by point, like the values need to be coherent, you need it to be continuous or even differentiable. And that's the added difficulty of doing differential geometry. And that's why usually that's why if you go on the Wikipedia page for musical isomorphism, they're going to say that you're not only on a manifold, you're on a Riemannian manifold, which is a spicy manifold. A spice. Yeah, I mean, the thing is that you...
Is it too early to say that I'm lost?
Yeah, basically you've...
This is rough.
The thing about math is that that requires a lot of background. But okay, so you're familiar with the notion of a vector space.
Well, yeah, basically it's well, no, I don't have the definition memorized, but it's all the different vectors you can reach for certain basis vectors, right?
Yeah.
Okay.
That's good enough for what we do. We're in finite dimensions. Everything is good. Hi, Lemon. I'm going to explain musical isomorphisms.
You don't, Lemon. You've. Oh, I'm so glad you're back. You've joined in at the perfect time. You're gonna like this.
All right. So, vector spaces. Yeah, linear combinations of basis vectors. That works. Not the best abstract definition, but works. Don't ask for much. When you have a
Oh.
vector space,
Yeah.
you can construct a new vector space called its dual. Why it's called a dual is because I mean, it's called that. There is notion. There's notions
The
of
reason
duality.
why
Basically,
the reason why it's called that is because someone named it.
I mean, there's like, I mean, it makes sense. For instance, when you've got a matrix, which is secretly a special function between some vector spaces. So this function gives you a function between the dual spaces that goes the other way around. And it's actually, and the matrix of this new function is actually the transpose of the original one. Like that's the algebra behind it. And like when you transpose once and then you transpose again, you end up with the same matrix. So there's kind of a notion of
Okay.
duality there. And so vector spaces, finite dimensional ones, are very nice because if you've got two vector spaces that have the same dimension, well, they're basically the same vector space.
Yeah.
That's the isomorphism part.
Okay.
So if we take any point of our geometric thing, we have a vector space like at that point that's tangent. And we have its dual vector space that's called the cotangent vector space. It's not really easy to picture it geometrically.
I can well I can't see that. That's the point, right?
Yeah, I can see it's either maybe if you've got like a 5-dimensional brain or something.
Oh, I mean,
I don't know.
or when you're high
The way I understand it
release.
is that the tangent vector space, it makes a lot of sense. Like okay, it's basically the idea of derivatives. Like you've got your sphere, you put a plane on it, and it's tangent.
Hold on, I would just like to say that you've just said theory of derivatives as if like the idea of taking a derivative of a vector space is just you know how it is in mathematics.
Basically, when you take a derivative of like a function in calculus, you're trying to basically the problem you're solving is you're taking a point and you're saying, okay, what's the line that
what's the
best
tangent
resembles my
at that
functions at this point?
At that point, but I'm sorry.
And here you're doing this, but in many dimensions.
I'm struggling how would that be tangent in. I'm struggling with that because wait, so a tangent vector space.
Like take a sphere.
Yeah.
Zoom in on a point.
Yes.
It looks like a plane.
Yeah.
So basically what you do is that you can attach, in a way, a plane to this point that looks like the sphere at that point. But if you zoomed it infinitely far.
And that is, wait, so, and that would be the tangent.
That's the tangent space at this point.
Okay, that makes sense. So it's basically
the thing
like.
Is that there's a lot of data to keep
Wait,
track
do you
of
lose dimensions? Yeah. Or do you not?
Nope.
Okay,
nope.
Don't lose dimensions.
Same dimension. Well, when you zoom in on a 2D object, it looks 2D. When you zoom in on a 3D object, it looks 3D. Well, 3D objects are actually hard to picture. Yeah, that's what I'm doing, Lemon.
Saying music from Lemon, you don't understand how much background I'm lacking, okay? You just don't understand how much background I'm lacking. So
But yes, so basically you've got
alright, tangents.
You've got one vector space for each point.
Yes. Okay,
so
makes
that's
sense.
Like a lot of data to keep track of, but geometrically it's understandable.
Yes.
Actually, there's even more structure on it, but I'm not going to go into that.
So that's kind of like if you have a function, that's kind of like having a separate function that's just a linear function tangent for every point of this function. That's like the tangent vector space at every point.
Kinda, but the thing is that we don't really tend to think about it as a function. We think about it.
I mean, I know. I'm just grasping at straws here. Okay.
Yeah, I think of it, but I haven't done a lot of differential geometry, but I guess the best way to think of it would be, well, as
would tangent geometry then? I mean,
I'm not gonna go into that.
Okay, so with tangent vector space then? Yeah. Okay, the way I think of it right now. Is it, because I know it's not gonna be great. I just want to know if it's any closer or further away. It's like if you have a vector space, you have an infinite amount of points that you can basically get to using the vectors. And if you zoom in on any specific point, that's kind of like, I can't find a better word. So you basically get a vector space. The tangent vector space would be the vector space that like approximates the vector space at that point. If you zoom in infinitely far, then you would not see the difference between the two.
That's it.
But
basically.
when you hold on, okay, so if you zoom further away, would those be different vector spaces?
Okay, so there's no really. I mean, if you change your point, you get a different vector space. Because like when, for instance, like if you, I mean, the vector space is morphic, but if you change your point, you get different vector space. But the thing is, there's no really notion of zooming less far because, I mean, I'm kind
It's
of
a point.
hiding it since the start, but there's a limit. So you zoom in infinitely far, and infinity minus a little bit is still infinity.
Yeah, I mean, or in other words, like you're zooming in at a point. You can't just zoom in at a bit larger point. It's still going to be a point.
You pick a point and you zoom in on it.
Yeah, if you make a point 3 times larger, it's not going to help.
Yeah. So you've got one vector space for each point.
Right.
Now, algebra tells us that when you take a vector space, you can think about its dual vector space. So if we pick a point, we can get the tangent vector space.
Yes.
And we can think about its dual vector space.
Yeah.
That's interesting because it's the thing that derivatives live into. Which, like, derivatives, a pretty big deal.
Yeah, I mean, I've seen them used once or twice.
Yeah, me too.
Like, a pretty niche thing, certainly,
that's why we care, basically. Like, I mean, that's not the only reason why we care, but I think it's already a good reason to care. Now, the thing is that in linear algebra, if you have just one vector space, and it's finite dimensional, but everything here is finite dimensional, then it's in a way the same vector space as its dual. So what you can ask, so what you know is that if you pick a point, you get the tangent vector space and its dual, and they're in a way the same. The question that's kind of natural to ask there if you do geometry is, okay, but like, can I bring geometry into this? Basically, the thing is that if you just pick a point and then do the algebra, well, I mean, you're kind of forgetting the whole geometry thing you had in the first place.
Yes. Jesus,
basically
rough.
Yeah, there's a lot of I mean, it's like, it's master. You'd learn about this like in the first year of a master's degree. Obviously, it's not easy to understand, and even when I did my differential geometry course, I struggled a lot.
I mean, yeah, the thing is, the problem here is that, like, your understanding of it is like a concrete building. Mine is just like, there's so much scaffolding attached to it. Yeah.
And the thing is, musical isomorphisms are basically what you get when you take this, when you bring geometry into what I said, basically. It turns out that if you have a geometric thing with a little spice on it, like a Riemannian metric or something, fortunately you can always like find one under some hypothesis, so it usually works, like most interesting cases. You can actually bring geometry into this, and actually I think I should get an analogy for this. It would be great. I'll think about it later. Basically, you can usually manage to actually basically what I've said is that you can do something for each point, but you like to do it for all the points.
Yeah.
In a good way. And what I'm saying is that most of the time, this works.
So like, wait, so like create a vector space of vector spaces? Is that...
Actually, the word you're missing here is called a bundle.
Bundle. I was about to ask if that's what the bundle is, because I can see tangent bundle and cotangent bundle.
It's not really a vector space of vector spaces, but basically, if you've ever heard of the Hairy-Ball theorem, or if you have hair, which you might.
I mean, the Hairy-Ball theorem has made its appearance on streams.
Basically, how you can think about hair is that you can think of like just your hair, but actually there's a lot more structure to it, because you can think of it as your cranium, and at each point, well, basically you've got a line, and the line is basically a vector space, and it's your hair.
Oh my,
that's what the data of a bundle keeps track
no,
of.
I
Obviously,
want
the general definition is much more general, and you can, instead of attaching hair, you can attach planes and stuff.
I want to go back to easy maths. I want just operators. That's all I want. I want
the
this.
differential geometry is like, I believe I found it hard, honestly, but that's because I'm not the best geometer around. Also,
no,
though I wasn't the only one. One of the teachers I worked for told me that back when he was at the same uni I was, he did math, then he went to physics, then he saw a physics thing where the size of matrices went to 0, and then he gave up and became a math teacher. That's so funny to me. But he also told me that the hardest course he took in his first year being there was the differential geometry course. When I say first year being there, I don't mean like as a first year undergrad, but like as you'd be the equivalent of your third year after high school.
By the way, said, how do you think we can incorporate the Hairy-Ball theorem in the penis CP spectroscopy? I think you can do it using the Cox-Zake machine, I do believe. That could help.
No joke, there may be... I don't really... and it's not that I don't really know, so I have absolutely no idea how spectroscopy works. But if it's... Yeah, spectroscopy, actually. I think I'm confusing it with something else. But basically,
I'm thinking about how
stuff like in stuff like MRIs, where you get a lot of data attached to geometric things and stuff.
I mean,
you can actually bring algebraic topology into this, so maybe you can use the Hairy-Ball theorem for stuff.
I mean, you could maybe use it with like... I'm thinking about... I'm really trying to fit a hairy ball into the penis, you know? I really want the hairy ball to be in the penis, but basically, because you wouldn't be able to do it with a group of atoms or molecules. I'm trying to fit it into the orbital in some way. That would help with a hairy ball. I really want a hairy ball in the penis. Try to find hairy ball into the penis, you know? Exactly, yeah. And screenshot that to best comments.
Some people asked questions in the chat. Do I play an instrument? I used to play the drums and I didn't really like it. I didn't have the needed motivation to like keep practicing, so I kind of gave up. Besides that, no, I'm quite bad with physical objects.
That's why you're only dealing with abstract ones. I'm quite bad with...
the most music I do will be musical isomorphisms, and that's like...
I do have to say that you are like the most mathematician. I'm quite bad with physical objects, is something that only a mathematician can say. I used to play the piano, the trumpet, the flute, a whole bunch of stuff. Guitar at one point, but only a little bit.
You should do an animation of MAKiT and his clones just playing a song.
Just jamming out,
100,000 subscribers.
Now I really want to make a video which would just be called like a short one, like a 7-minute video, just called "Penis in Chemistry," and like about different spectroscopy methods. I mean, whoa, no, actually, "Penis in Chemistry" would go hard as a video. Hold on. Oh, this, but
It may become the most viewed video.
yeah, it may actually become but the thing is, I would only make it about different. I don't know if I would even fit in all the other spectroscopy methods. Hold on, penis spectroscopy, and just in case, I'm gonna look it up on the other screen because I feel like that's still too vague. Cross polarization. There we go. Proton-enhanced nuclear induction spectroscopy.
Free energy exists. Yeah, actually, when energy is not enslaved, it's free. and the physicists enslave it to.
The thing is,
their bidding, but...
I love how, by the way, it's in physics. I love how really often physicists will just like find a fun tool in mathematics, and they will just bring, and they clearly end up loving it so much, and you can see like the childish joy of using it absolutely everywhere. Like when physicists when some kind of mathematician told physicists about the fields, basically just fields, just broad idea of fields, physicists just went hog wild using absolutely like, the thing is, that's not even my example, but you can consider the entire universe a field of Earth, where everywhere that Earth is has just the value of 1, and everywhere else is just the value of 0. Which
we're inventing characteristic functions, they're called in English.
Yeah, but no,
they're like extremely useful in like probability theory and all the stuff I don't do. But nice idea. We would have gotten like a pat on the back for that in the past.
That's the most clickbait title. It's not wrong, it's penis in chemistry. That's what it is. I'm not lying. Listen. Shame me if you want for for standing up for what I believe in. I believe in the penis. I believe that the method works. That's what I believe that the penis works, you know? I would like to use the penis, huh? I would. I feel like but at the same time,
Doug, but no, you don't play a bong. You smoke it.
You know what I think, by the way? I know it's chemistry's not quite math, but I feel like that I could actually do better than this. Yeah, I feel like my penis would work better.
Glad to see I still have the humor of an average 8-year-old.
I mean, yeah. They called it the penis reflex. The researchers that made up, they called it the penis.
That's the physics department. What did you expect?
I mean, the thing is, it's hard to say that I have I have a humor of an 8-year-old when I don't know how old they even were. Like 40-year-old researchers called it the penis.
Yeah, but MAKiT, you're actually 8 years old, so
yeah,
I'm sorry, chat.
That's age appropriate.
MAKiT told me actually was 8 years old. He showed me his ID and stuff. He's actually
my 8-year-old ID. My 8-year-old ID.
Could use a spectroscopy of flame penis vlog when
we want the flame penis lab tour. That's what we want. We just want to flame. Listen, it's not weird. We just want to see your penis, okay? I don't know what to tell. I'm just really into chemistry, you know? I'd be amazing. It'd be amazing to have an excuse to use the word penis in all caps throughout your PhD. It really would be. But then, you know, the 1984 non-fun loud, they changed it to CP.
There's an actual it's accidental, but there was a researcher in like algebra and group theory that's actually French. It was called Jacques Tits. So you've got the Tits group.
Tits group.
Look it up.
Hold on, I'm pasting a best comment. Tits group. You know what? No, I'm not gonna look that up. Like on main screen. Give me a second. Mathematics. Let me specify. I feel like if I just look up tits group, I'm not gonna get quite what I'm looking for. It's a tits group. Chuck's tits. Like this, so I'm not gonna look up tits group. Just
and also like it's a legitimately interesting groups.
Wait,
Group like
wasn't there like some? Oh, there was some mathematician. I don't remember who that was. Where their name was. My brain is empty at this point, but I remember there was
What's
some
his
mathematician whose name like was something like group or was something like set. I don't remember. It was some mathematical term, and so
I know there was a guy named Robert Singleton, which is funny because one element set is sometimes called a singleton, actually all the time in French.
yeah, but there was someone like it, and I remember that they created a completely unrelated thing. I remember nothing about it though.
Do you remember like in which general area where the things
I
were in?
do not. Someone told me about this on stream months ago. I had to look it up, and I remember it was funny. But that's all I remember. Damn it! Who was it? Fuck! Now I'm gonna be.
I mean, maybe I can just like go look at a list of mathematicians. So apparently, mathematicians from the German Empire is a whole category.
It's so upsetting because I remember someone telling me about it on stream, but I don't remember what their name was. It was something like group set or something like that, where basically it was their name. Damn it! I don't remember what it was. 13C CP mass spectroscopy used in one of my PhD professor's papers. So he used penis before. That's impressive. Listen, it's one thing when it's self-reporting, but when you write a paper about how you're using a penis, I'm impressed with that. Isn't there something called CP symmetry? Yes, there is CP symmetry breaking, which is even funny, I think. CP symmetry breaking. CP violation, there we go, that's what it is. It's the CP violation. Also what happens.
I found a mathematician called Bernard MAKiT. We are this close, guys.
One thing in mathematics I'm proud of, which I'm not really proud. I'm not proud of it because it's gone nowhere. But if there's one thing I would like to resume, it is the hyperoperation. Because the thing is, that's why I want to invite some more mathematicians for this one. Because to me, if it would turn out to be true, it would be such a cool thing that you could basically describe any transcendental number with a finite amount of mathematical operations with just finite hyperoperations, which is
yeah, MAKiT, you're not going to be able. Well, it depends on what you mean by almost every transcendental number, but
well, no, because the hypothesis would be that every is just that a finite number of hyperoperations. The only problem is that those hyper operations would have to be like could be infinitely of infinitely high order.
Oh yeah, if they're as long as they're uncomputable, that seems legit.
I mean, yeah. I mean, obviously, they obviously can be uncomputable simply because like square root of 2. Is that computable or is it not?
You can, by computable, we mean that we can like create an algorithm that gives us the digits of the number. So yeah.
Oh, so
for square root of 2, it's okay. It's just that most numbers are actually not computable, and you can probably find a number.
Yeah, the thing with real numbers.
Find a number that if you could compute it, you could decide if math is true or some wacky ass logician stuff. Logic is a bit scary, honestly.
Is the whole thing where real numbers are actually by default transcendental,
Real
or
numbers are
actually,
like
by
big.
default they are. Isn't it funny how most real numbers are like indescribable, where you cannot even create a description of them? Like,
I try to not think about it.
I mean, to
love
me,
real
it's kind of cool
numbers.
that's 0 point and then just random numbers forever. Like, that's an indescribable number. You cannot describe that number in any way. And most numbers are like that, where actually all the ones we can describe are an infinitely small sliver of them all. I find it funny. I like it. I give a fuck.
Let's see.
How did we get from musical isomorphisms to French tits? Well, that's never a big leap. You know how I like it. I like it with my hairy balls, my penis, and my French tits. That's how I like it. And CP violations.
Maybe don't say that.
What do you mean?
Nothing. I just have an irrational hatred of CP violations.
No, it's actually extremely natural for a CP violation, you know? It's really natural. It's fun. Yeah, it is. It's just...
I'm trying to like browse through laureates of praises of some kind because, like, with any chance no, if it's really old mathematicians, they weren't praised still. Oh yeah.
Oh, don't go through that.
My approach is flawed.
This is a... You mean with the... Wait. You're still looking for it?
Obviously, I'm looking for it.
I mean, mate, that's like a random thing I've learned from months ago. Are you really gonna pass like every single mathematician in existence?
No, because unfortunately I'm not immortal yet.
That's precisely my point.
No, but I'm like quickly looking at the people who actually have a Wikipedia page, so that like that's already
That's
a subset
still a lot of people.
everyone.
I mean,
If you're only looking at the names, it takes less long.
yeah, correct me if I'm wrong. Integers are a subset of real numbers, but I feel like going over all integers still wouldn't exactly be quick.
Depends. Do you allow time? Do you know how to time travel? Yeah. I
Don't
know,
bring
I'm
in
not
countable
familiar.
infinities into this.
I know that like there were some people that like got, and how do I say this? Basically, when you take the competitive exams to like get into my uni, basically a list of people that like get ranked and stuff. They're public, and sometimes you find funny names.
I mean,
There was a guy named Euler, Euler, a few years back, and he didn't get in, so I don't know where he went. There was another guy that had a funny name, but it's for a French reason. It's not really a math pun, and I don't really like want to explain the whole school system.
Oh, another thing, I don't know if you're familiar with it. Are you familiar with Euclidean zoning?
Euclidean zoning.
Yeah, it's a thing. It's not really mathematical, but it's a... I mean, kind of. It's a type of zoning. It's like a way to zone cities. You know why it's called Euclidean zoning?
No, why?
Well, obviously, Euclidean. Duh. It was named after a town in the US. Euclidean zoning.
It's just history.
I think in the US, but yeah. And it's just funny because the Euclidean zoning and has nothing to do with Euclid. Euler no, not Euler no. Only maths.
Euler fans.
Euler funds.
How about Euler fonts? There's actually a math font in LaTeX called Euler.
Of course there is. Like, give me one thing in math that
really
isn't called Euler.
Not really Euler, like Euler VM, but you know.
Name me one thing in math that isn't called Euler. Everything is just called.
Sorry.
Actually, Oiling
No,
up
but
lemon.
if you go deep enough, in, I mean, like the thing is, a lot of things at a quote unquote basic level, not really basic, like Euler did some really non-trivial stuff
I mean,
for his
yeah.
time and even now. But once you get to like, for instance, algebra wasn't really invented when Euler was around. So
Yeah, because he died before
there's
he invented it, honestly.
yeah, it's a different mindset than analysis. It's kind of like, how to explain this? The idea of analysis is, well, I mean, you know what it is, but the idea of algebra is more like to kind of figure out what's missing and what new definition would be a good one to consider. The thing we had to do when we like invented zero and stuff.
When it comes to inventing like that, what I think is funny is, I know it's completely underrated to once again, but I just love that fact so much. Do you know Al Gore?
The programming language?
No, the person who was trying to become president in the
Al Gore,
2000. Yeah. What's really funny is that I learned that from Climate Town, I think, where Climate Town did like did the joke of the kind of where it's like, and then Al Gore said to post it on the internet, and they asked him like, "Hey, what's the internet?" And he said, "You'll see," because he hasn't fucking invented it. And I just find it so hilarious. If you go to Wikipedia, like one of Al Gore's achievements there is just inventing the internet. That's what it's called. It's just there. Let me show you. If you go to Wikipedia of Al Gore, right here, then I think it's second presidential round, inventing the internet. It's just there. Like, as a side thing, motherfucker he was running for president, and as a side hustle was inventing the internet. And apparently, one of his sayings was that, hold on.
During my service in the United States Congress, I took the initiative on creating the internet.
Yeah, hold on. Take it. Oh, there we go. Where basically one of his rejected campaign slogans was, "Remember, America, I gave you the internet, and I can take it away." Which, I mean, is such a power statement, honestly. Play nice, I'm gonna take away the internet. Knot theory is just funny.
Relax, I won't explain why, but being a fellow degenerate, you may know why. Knot theory is just as funny to me as the penis and tit stuff, Omeo.
Have you ever like seen, or have you ever delved into knot theory? That's very aggressive typing.
Oh, I have a funny story about that. Actually, so I haven't formally done knot theory because it's kind of niche. I mean, it would most likely
It's
interest me, but
extremely niche. I mean,
I'm more of an algebraist than a true geometry boy, so you know.
yeah, that's the thing. It is.
At one point, I briefly considered like doing my internship on. There's analogies between number theory and knot theory, and I asked my advisor, and he said, "Yeah, so this is extremely niche. I can only send you to Japan or the US." And I was like, "Yeah, no, it's too far."
Because the knot theory, I would say knot theory has the most similar approach to topology. I think, I would say.
Yeah, it's definitely. It would be a part of what we could call geometric topology.
Yeah.
To differentiate, to like separate. We call it geometric topology to. Like when we say topology, we could mean like general topology, which isn't really very geometrically flavored, since the interesting part of general topology is that you've got lots of very bad behaving spaces that look like nothing. We could mean differential geometry, which is the interplay of topology and differential geometry, or geometric topology, which is mugs and donuts and stuff. And knots.
I love how I just love how abstracting in math works. I just find it so hilarious. Where like topology, yeah, it's simple. Like imagine the donut. Topology is simple. You just ask a question of how many holes does a donut have, right? It's simple. Okay, now imagine that you don't have a donut, that or rather that your donut is not actually a donut, and it's not actually a three-dimensional object, and it doesn't actually have any holes. And now we ask the question of how many holes it has, but they're not actually holes. They're just like there's an abstract concept of a hole. Welcome to mathematics, basically. Imagine the space. It's not really a space. But...
The reason why we call, I mean, I think it's like just bad names of stuff that's stuck around.
I mean,
but general topology feels like when you learn it first, you're not learning it for geometry. You're learning it because every branch of math uses it in some way, and actually, it feels a lot like analysis. It turns out that it's actually practical to use as like building blocks to do geometry and stuff with, but doing like learning geotopology and the concepts from it, they feel like a lot of analysis, and it's the reason why we don't just teach it right away is that it's so much easier for the brain to understand and wrap its head around it if you've done analysis before. Another typical. One time I saw a video describing holes with derivatives and the typical idea of a hole, which was spark confusing. Oh, all right. So that's an amazing thing, actually. No, it's kind of crazy actually, and I still haven't read the proof of it. I should once.
Wait, one the whiteboard, by the way, before you get to it, because I.
No, I'm not going to go into a deep explanation because I need to sleep at some point.
Oh, that's fair.
Basically, we have like some tool to understand how holes work in like topology, algebraic topology. It's myself. It's called cohomology. I'm not going to try and explain what it does because it's hard to define stuff. I mean, honestly, in retrospect, it's alright. The basic idea of homology is actually not that hard to conceptualize, but the mathematics behind it are hard. But for good reason, is that it's extremely computable. So it's a really useful tool that works really great to understand the structure of spaces. And we've actually got a thing that looks a lot like it, but this time it's in differential geometry. It's not just topology, you really need the differential part. Basically, when you do differential forms, you've got the property that if you do the derivative 2 times, it gives you 0. And this kind of property makes it look a lot like cohomology. And so we've got something that's called Duran cohomology because it was studied by some guy named Duran. And it turns out that both things are equal. And that's like kind of crazy because the first thing is purely topological. It doesn't care if your space is smooth.
You see,
you can have sharp points and stuff.
When you lose
the other one is purely like analytic.
Yeah, you see, where you lose me is when you said one thing is topology, the other one is purely analytic, and you're saying like they're equal. That's kind of, yeah, that's where you lose me.
I can make it more concrete.
I felt for a second you were about to say I can make it more confusing.
I can also make it more confusing, but I want to explain better. Basically, the theorem allows me to say that the reason why there isn't a complex logarithm is because if you take the complex plane and you remove the origin, it has a hole. And that's like the actual reason.
That's it. I mean, okay, I won't sit here and pretend as if I know why that works, but just honestly, going with it, that's insane.
To know, even though I don't know all the details yet.
Going with it,
to learn at some point, but basically, it's that.
That's insane. That is just insane. Wait, hold on, just to make sure I understand. You're removing for logarithm. You're removing the origin because you can't reach the logarithm, right? A complex plane.
You can reach it with the exponential, yeah.
Oh my, that's actually pretty sick, I have to say.
Yes, that's yeah, and that's actually like I'm not exactly sure about that, so maybe it's not true, but I suspect that the reason why the logarithm
Educating us.
works good on R is because R doesn't have the exponential on real numbers it gives you positive real numbers and there's no holes there. I think you could probably like say something about that. I should I mean, I'm reading like an algebraic geometry book, and that's not really algebraic geometry. It's more analytic complex geometry. But you know, it's one of the examples that the guy uses, and so maybe in like, so maybe when I'll be like at least 60% more insane, I'll understand it perfectly. I know, like I know it's one of the favorite things. It's one of the favorite theorems of one of my PhD student friend. But he actually does number theory.
Also, Lemon said something
He
specifically
does number
directed.
theory, and the other day we were like talking in the where there's couches to sit on stuff, and we were talking about one. He said people who do number theory are weirdos.
I mean,
And there was like my topology professor who does probability theory for a living. He was passing by and he said, "Oh yeah, that's true."
by the way, Lemon has a question, or rather, statement. Fun fact directed at you.
Pinged me also.
Yeah.
Is someone who hates cohomology considered cohomophobic? Honestly, I think if you don't like cohomology, it's because you probably don't like homology, so you're never going to get cohomology in the first place. So you're truly homophobic. Right away. Oh, fun fact: the pentangular three-space difference they're going to use is so important to cohomology. Do you need Durham cohomology to make it work? I mean, obviously, I know it can pop up like quite easily, but does it actually use it to make the whole thing work? Hold on. All right, I found it. I mean, I know that there's secretly Durham cohomology hiding in there, but for the diagram to work, for the pentagon part, you only really need to know. Wait, you're in a manifold. That's is what I'm saying correct? No, yeah, it makes sense. Makes sense. Yeah, it does include the chain of exterior derivatives. Yeah, obviously. So there is the cohomology hiding in there. But the only algebra you need to really make it work would be, well, linear algebra, basically. Linear algebra and trusting that it goes well with the geometry. But yeah, basically how it happens is like there's, if I'm not mistaken, I've heard a lot of times that in the algebra biz, people are basically trying to make a homology pop up everywhere, because homology is like well, it feels a lot like black magic. Not really, because I understand it. Logic feels like black magic because I have no idea what the fuck they're talking about. But basically, homology is a very convenient tool to understand geometry, and it's very, very algebraic, and it's very, very computable. And we've thought a lot about how we can calculate it. So it actually tells us things. That's the big thing. Like in algebraic topology, basically we do algebra to understand how holes work. Well, topology really, but it's mostly holes. And we've got like two big types of algebraic constructs we can do. We've got homology and cohomology, which are more or less the same. They're kind of hard to define, but they're very, very computable. But they technically don't tell you that much.
I just wanted to say that because
and on the other, yeah.
Actually, I don't know. Do finish. I'll.
And on the other hand, you've got homotopical invariants, homotopy groups. So basically the simplest spaces we can think of in algebraic topology would be spheres in, well, in not just the spheres you know, but spheres in any dimension, because, well, obviously. Remco stops at 5. I just don't stop. And the thing is, the homotopy groups of spheres, we have no idea how to calculate them. Actually, the main purpose, homotopic invariants, homotopy groups have two main purposes. First, they're very hard to compute, but theoretically they tell us a lot of things. And second, because they're so hard to compute, they give a lot of algebraic topologists a job. Yay, employment. Now that I've created the problem, I can finally be paid to solve it and fail. Yeah.
I just wanted to say, because Lemon said that I still find it really cool how I'm learning this stuff super ahead of time. I don't exactly like that comment, because that comment sounds like, Lemon, it sounds like you're assuming that it would be normal to, like, for someone older to learn this stuff, which the thing is, I don't think age is the problem for musical isomorphisms, to be honest. I feel like you just need to be that kind of person. You need that level of mathematical insanity to get into musical isomorphisms. You just, yeah, you could have an 8-year-old chemist. It doesn't matter. You need that mathematical insanity gene there. The thing is, I've seen you both talk about musical isomorphisms for such a long time, and I always read these comments, but I, to this point, don't know what they are. Like, you right now, you've joined in and tried explaining them to me, and
it's, I mean,
I don't know if we should try again, because I don't think it's gonna work.
I think there's like there's kind of like two camps in mathematics. There's two sides to mathematics. On one side, you've got the side I'm not on, so I know a lot less about it. Is the side where there's people that do like partial differential equations, combinatorics, probability theory, and so on and so on and so forth. And so these are the people that like they need less theory. They're more interested in like actually solving problems. There are people who are problem solvers. The prototypal example would be Polar Dosh. Because basically his life was doing math, solve problems, sleep at work colleague's house, repeat. And he solved a lot of problems. Real lot of problems, and he mostly did combinatorics, graph theory, a lot of discrete math, basically. So these are a lot of areas where basically the barrier to entry is not that high. You don't need a lot of theory to understand the problems or even just do work, but you need to have big ideas. You need to have clever insights. You need to be clever. On the other side of mathematics, the one I'm more on, and I'm a moron, remember that. You've got algebra and geometry and all the related stuff. Group theory, Lie theory, algebraic geometry, differential geometry, p-adic geometry, a lot of algebraic number theory. The number theory has foots in both sides, because you also got analytic number theory, which feels more like solving problems. Theory builders, on the other hand, the prototypal example would be Alexander Grothendieck. Why was Grothendieck famous? Well, first, at the end of his life, he went insane, so obviously that's a good sign.
Yeah, that's just
Second,
part of the course for mathematicians, I imagine.
second, basically, so actually he started out doing functional analysis, which is absolutely not where he ended up in. He ended up in homotopical algebra, algebraic geometry, mostly algebraic geometry because he fucking invented it. Not really, but he invented the modern form of it, basically. And he actually did that to solve conjectures in number theory. But he started out in functional analysis, and he had two thesis advisors, and they gave him some problems, and they said, pick one for your PhD. And he came back like months later, and he solved all of them. So he was obviously like good at math, and he just worked a lot and stuff. He actually like invented measure theory on its own, on his own, because it just interested him, like when he was an undergrad, and stuff. Why was he clever about the whole algebraic geometry thing? Well, basically, there's a quote by Jean-Pierre Serre, the same guy that said the thing about mathematics and physics and God. Serre also worked in algebraic geometry along with in algebraic topology along with Grothendieck, and basically he said that basically Grothendieck invented the main objects of study of the field. They're called schemes, and I'm not exactly sure what they are, but maybe I'll know in like 2 weeks. If you actually understand the definition.
Literally just scheming, but carry on.
And what Jean-Pierre Serre said was that the definition of a scheme was in the air. Anyone could have come up with it. The thing that was different with Grothendieck was that he was actually trying to come up with stuff. He wasn't trying to solve the problems directly, he was trying to build a theory and just let the problems dissolve themselves and become very easy to do with theory. So that's basically that's the thing. Like when you do differential geometry, the definitions are very concrete in a way. Obviously, no, I'm lying too. They're very abstract because it's math. But you can really see how stuff works. When you see the analog of what a manifold is for an algebraic geometer, you're like, because you just had to learn category theory and sheaf theory and a lot of commutative algebra to just make sense of the definition. It's a huge change. It basically completely changed your point of view on stuff you know. And for instance, if you want, there's something that I don't understand yet, but it seems very cool to me. When you do algebraic geometry, it's easier to construct the cotangent spaces rather than the tangent spaces for some reason. Do it backwards. because of the whole change of point of view thing, basically makes you go the other way. And so there's really like two kinds of mathematicians. There are people who solve problems, and there are people
Wouldn't that
who
be
build
just
theory.
like theoretical mathematics and practical mathematics, where theoretical mathematics is responsible for creating theories and practical mathematics is for applying those theories on problems?
You can kind of think about it like that, but if you call it theoretical mathematics and practical mathematics, you're going to have some people that complain that what the practical people are doing is very abstract and not practical at all.
I mean, to be fair, like, practical mathematics is still... It's kind of like when I joke around that Flame is doing practical theoretical chemistry. Like, practical mathematics would still be theoretical as mathematics, but in comparison to theoretical mathematics, it would be practical.
Farm, I mean, this may be pushing the borders of what's allowed here, but mathematicians need to define holes because they aren't getting any. Well, obviously I'm not. Y'all don't have enough holes.
Honestly, a wild burn, you know? It's not that I'm not getting enough holes, it's that you don't have enough for me. Which is gross.
There was like an amazing jump scare joke. It was, don't worry, it's a hole again. How so? It makes holes.
Isn't that like the version of Tomska's joke where it's, oh, don't worry, this is a holy gun. How so? It makes holes. I think it was Tomska
Yeah,
in the beard sketch, if I remember correctly.
yeah, that's the one.
Tomska's great. I love how I'm switching different topics because when you talk about mathematics, I'm just sitting here in the corner like I have nothing of value to add. Whenever you start talking about the subject, I just go silent and just listen because I have absolutely nothing of value to add.
I mean, that happens to me on like almost a daily basis with the people who know more math than me.
I need to
Uh,
get more into
Actually-
practical mathematics because then I could because that would be like the easier branch for me to like get on a level where I can actually start a conversation with you.
I mean, yeah.
Just
But
like
I mean, honestly, this point of view of splitting mathematics into two distinct areas is, I mean, it's obviously an oversimplification. I guess
always
maybe
is.
the slightly more true model is that at any given point, you know some amount of theory, and you've got fields that need a lot more theory than other fields, and you've also got your interests that differ. Do you want to develop more theory, or do you just want to solve problems by applying the theory?
Yeah, I mean,
And
whichever
that's how you
approach, I mean, that is like the ideal approach, isn't it? When you have a problem, if you develop a theory for the problem to solve itself, that's basically like the golden standard of what you can do in maths.
actually, like when you do homological algebra, so that's the very algebraic, very abstract part, the abstract nonsense part, basically, of computing homology of stuff. When you do homological algebra, you prove some theorems. They feel kind of like magic. Like you prove one lemma that's called the snake lemma, and then you just apply it repeatedly. And the snake lemma is easy to prove actually once you know some linear algebra. And then you just apply it repeatedly, and stuff happens. The machinery works great. Basically, you're kind of like a wizard wielding some magical scepter of homology. But like, for instance, the thing that's very cool about homology and that makes it extremely computable is that when you've got a space and you want to understand how it looks, a thing you may want to do is maybe break it up into smaller pieces and try to understand how they work together. So for instance, to understand how a sphere works, what you can do is that you can consider it as basically two disks. A two-dimensional sphere or usual sphere, you can consider it as two disks, but kind of glued together. So the two hemispheres, basically.
Yeah, I'm assuming you're going somewhere with this because, to be honest, like out of context, this to anyone who's not a mathematician, out of context, this would be hilarious.
The reason why that's the reason why that's a clever way of doing stuff is basically because a sphere obviously has a hole. Like visually, you see that it has a hole, but the two disks don't. And when you actually like apply the algebra, you get what's called a short exact sequence, and algebra turns it into what's called a long exact sequence. I'm not going to even begin as to explain what they are, but basically the thing you want is that you want a lot of zeros in your exact sequences because it makes the computations very easy to do. It requires no thinking, and thinking, well, it hurts my head. I don't like it. And so the thing is that basically stuff being zero in the exact sequence, well, the stuff is actually the homology that encodes how holes work. So if something has no holes, it's going to get a lot of zeros. And well, that's the cool part. If you manage to break up your geometric thing into smaller components that are very simple, well, the whole complicated business of how they fit together is actually handled not by you, but by the algebra. And so you just like write out some.
So it's like basically just it's
Yeah.
it's no longer a problem because I
Yeah,
mean
you
it's
don't need
just
to think about
it,
it. It's just automatic.
yeah, it just
That's the
becomes
beauty
like
of
an
it.
obvious. Okay.
The only thinking you really need to do is to think about how you're going to approach this problem. So
I feel
basically, the only geometric thinking you need is to notice that the sphere is just two hemispheres.
I just want to say that
But
I'm a little bit.
the nitty-gritty details of understanding exactly how stuff fits together, you don't do it. You do it once by abstract nonsense, and then you use it for the rest of your life. It's beautiful.
I do want to say that I'm a little bit insulted because Lemon just asked me if I know what basis vectors are. Like I've explained what basis vectors are in 3 separate videos. One of them, which hold on, let me do. The thing is, the reason why I explain so much is because of explaining how matrices work is probably one of my favorite things to explain because it's so easy to explain matrices when you visualize them. Because I've set up the geometry nodes once, I can reuse them, and I always do it with basis vectors and just hold on. This one explained I've explained basis vectors. In this one I've explained basis vectors. In I think this one, that's an old one to be fair. Oh, this one certainly. You can even see in the thumbnail my beloved matrix. Funny enough, right now I'm gonna do some math for geometry nodes, but there's gonna be practical math, so it is gonna be different.
Also, I'm going to say one last thing before like go to sleep and stuff. The one thing I thought about like at the beginning when I came on stream, which was when we talked about like proofs and the intuitive ideas behind them. Actually, not long ago, I found, well, not me, but I came across on the internet a new proof of a result I knew, which is a very classical result in algebraic topology, which is, again, a computation. Basically, how to understand that a circle has one hole. I promise you it's interesting. But basically, you know, I said prior that you've got some homotopy groups that are very hard to compute. The first one is easier to compute. We've got some stuff that works kind of okay. It's called the fundamental group. And it's usually the first thing you learn about if you do an algebraic topology course because it's easy to define and actually doesn't require that much like algebra or background stuff. It's very concrete. Like geometrically, you kind of feel like you could have come up with that. Whereas if you like learn homology, you usually don't feel like you could have come up with that. Which is funny because historically, Henri Poincaré invented both of those and he invented homology first. But he didn't do it the modern way, so you know, the modern way is better, but it's also harder. But yeah, basically, you prove that some group is actually the group of integers. And the way we do that usually, like the classical proof that everyone sees in their first algebraic topology class, and that's like the first calculation you do. Without that, it's very hard to compute stuff if you don't know how to do it for a circle. Well, not really exactly the first calculation, but it's the first interesting one. And the usual way you do this proof is that you actually introduce a lot of theory about something other, something called covering spaces. And basically, it's actually the complex exponential. Is the interesting part. If you take the real line and you can map it onto the unit circle in the complex numbers with the exponential map. And like it.
Wait, hold on.
Kind of
repeat that sentence.
Yeah. If you take the real numbers,
right,
and you, well, it's not the exponential, but basically if you've got a real number theta, you send it to e to the I theta.
Yes, okay, I'm with you so far.
that ends up on the unit circle.
So map real numbers on the unit circle.
Yeah.
Okay.
And what it does geometrically is that it's kind of like if the real line wasn't really a line but a spring, and you were kind of projecting it onto the circle. Because every 2 pi it repeats every time
Like
you go around
oscillating,
the circle.
you mean? Or wait,
Hold on, I probably have an image for this.
I mean, the spring lost me. I'll be honest.
Yeah, you need to do to do geometric stuff. You need pictures, but hold on, I'm going to get.
I mean, I can try to imagine it. I don't even know, but I'm pretty decent at like imagining.
Honestly, picture is much easier, but yeah, it's probably a good exercise to try and imagine it. Yeah, I've got it.
Hold on.
Where can I send it?
MAKiT would study homology extensively. I'm just interested in mathematics, the thing. Right. Oh, that's not in what way I imagined it. It's okay. That is absolutely not what I imagined.
How do you interpret this? So we've got the unit circle on the bottom.
Well, imagine it is I interpret it as like taking the real number line and like spinning it into a coil. Except
yeah, exactly.
Okay, yeah, all right.
But then when you take theta and you send it to e to the I theta, it's kind of if you were flattening the coil.
Yeah, you flatten it
into the circle.
You flatten 3 dimensions into one.
Basically, if you do a lot of very detail-heavy topology, you can understand the structure of the circle in a very good way from just the structure of R and the fact that you've got the exponential, basically. And from there, with a lot of theory building, you can find out you can calculate the thing you want to calculate. But the thing is that there's some cleverness here, because you need to invent the whole theory you need to do that. And it works very great, and it's actually a very important piece of theory, but all that for just one calculation that seems like it's obvious, because when you understand definitions, it really seems like it should be obvious. That doesn't feel very satisfactory. The new proof I found on the internet is much more in line with the whole philosophy of taking the circle and cutting it apart into multiple pieces and putting them back together. The catch is that usually we don't do that because we don't really know how to do that with the fundamental group. You actually need something a little bit more algebraic called the fundamental groupoid for this to work. But if you just accept that you can do this a little extra step of algebra, well, you've got yourself a proof that feels a lot easier. It skips a lot. It's a little bit algebra. It has a little bit more algebra, but it skips a lot of. It doesn't need the real. It's easier on the topology side, basically. And so that's actually something. When I was looking at some papers, I wasn't reading papers. I can read papers, but I was kind of looking at what potential advisors would do for like my internship. I recall seeing a paper where some guy proved something that was already known, but he said in the abstract that the proof seems to him to be the right one. And by that he meant there were no clever tricks involved. And so that's basically what we're talking about at the start. If you've got a proof and something doesn't have an interpretation, usually what you try to do is you try to look for a better proof. Stuff is more natural, even if it forces you to build more theory. Actually, that's something I try to do on a limited scale. Like, for instance, in fact, what I've got written on my whiteboard here actually is we did a proof in an exercise session using matrices. and it was kind of clever. And so I tried to find a purely algebraic proof without matrices, no clever tricks involved, just algebra. And I haven't succeeded yet, I hope. But yeah, basically, if we don't know how to do stuff, we will resort to clever tricks, and once we have the clever tricks, we will try to get rid of them.
I do have to say that there's no thought that crossed my mind. I will be terrified of your PhD. Like, the thing is,
Oh, but don't you know, MAKiT? I actually have a slightly above average tolerance to algebra and abstract nonsense, so don't worry. Even the other math people will be terrified.
yeah, I mean, the thing is, like, it would be, I imagine it would be painful to other math people. To me, it would be lethal, basically.
The running joke among my friends is that I like category theory. And that's actually funny because I'm always the one like drawing diagrams and stuff and trying to do as much algebra as possible.
I would just like to say that if the running joke with your friend is that you like category theory, like, not even the joke itself, the fact that that is the running joke, that tells you everything you need to know.
No, but it's basically, yeah, it's basically it's a running joke about like the three friends I do algebra exercise sessions with. Like, we just take the exercise sheets and we just go to another room and just claim the blackboard for ourselves and we do stuff for 2 hours. It's great. We're like 4. We've got one guy that's here because he likes algebra and actually he's gonna do combinatorics, concrete stuff. We've got one guy that likes algebraic topology, so he's a more geometric version of me, basically. And you've got a friend that just likes algebra and doesn't really know what he wanted to do, so he asked to discover the algebraic geometry. So actually, he's going to end up like me with category theory. You can really avoid it. Actually, like my PhD friend, my PhD student friend told me that when you do math, you work with at least one of the following. Either it's categories or it's measures. So pick your devil. Okay, measures are probably
No one
easier,
wins.
but I don't know, my brain doesn't work. My brain doesn't process them the correct way to like be actually able to do stuff. I still think it's really funny how you can derive the formulas for U7 and Jacobians through wedge products. Actual lemon, I don't think you can. I'm not sure. Actually, you can do it with only wedge products because when you learn how to integrate differential forms, you need to know how to integrate stuff over the real numbers, if I'm not mistaken. And so you're going to need to like use the Riemann integral or the Lebesgue integral at some point. And maybe you need to prove the U sub formulas for these integrals before you can generalize it to differential forms. If you know, that's really cool because every proof using the Lebesgue integral is a hassle, but example I sent in the server. Where's your example actually? From where is it? Oh yeah, this. Some variables, differentials, since thing, which product this stuff, or this. Yeah, I see. Do you really need There's actually a pretty nice geometric interpretation of this, which is basically when you're differentiating something, you're trying to approximate it by simpler things being linear maps, but no spoilers. And when you try to understand, and the integral is supposed to be like the area under a curve, and so integral in more dimensions is supposed to be some kind of volume. And when you try to understand what a linear map does to volumes, well, actually you're inventing determinants. And so that's why the Jacobian is actually a determinant of a matrix. You're literally looking very close to a point, trying to understand what happens to volumes at this point, and then you're integrating over all points. That's why a determinant pops up, geometrically speaking. And that's pretty cool because when you, like, all the details in the proof, or when you try to prove that's actually what happens, they're quite cumbersome, but the idea of the proof is pretty nice and pretty natural, actually. Anyways, I think I'm gonna have to go because I have.
That's fine. That's fine. I get it. It is also really late, isn't it?
Yeah, you're in the same time zone as me, if I remember correctly.
Yeah, it's quite late. But unfortunately I can't go. I have to play with my balls. That's important. Takes precedent.
Don't forget the PNS.
Exactly. This might be some. No, it's not gonna be cool maths. It's gonna be just usual geometry node bullshit. It doesn't work even though it should work, and I'm upset.
My PhD student friend sent me. He told me, drinking game. Go to a number theory talk, and every time the speaker says that we don't know how to do something, take a shot. The way I understand it is that in number theory, absolutely nothing works. These integers and rational numbers are actually like so ugly. We need to build lots and lots of theory to do even basic things such as like Fermat's last theorem. And when you ask a number theorist what they do in life, they'll probably tell you that they try to do something and it doesn't work. But that's life, you know.
Number theorist. That's number theorist life. But I love the the dedication is what matters, at the end of the day.
It's quite funny because like my PhD friend was actually a geometer at the start. It just got sucked into number theory because it's well, when you do
Well, I imagine
algebraic
mental illness.
we're all mentally ill. We're all mentally ill here. When you try to find someone from the math department who's mentally sane, you struggle a lot, and I know because me and my friends have tried. We don't count ourselves as mentally sane, by the way, for obvious reasons. But yeah, when you do algebraic geometry, actually, some differential geometry people accuse algebraic geometers of lying and actually not doing geometry. So yeah, they just do number theory and pretend to do geometry.
they just call it like geometry terms.
I've seen someone on the internet saying that algebraic geometry is the study of stuff that kinda behaves like geometry.
I mean, it's not wrong exactly, I would say. I would say it's pretty accurate.
I don't know much, but I think it's really the way the people who do number theory with algebraic geometry use it. Anyways, I think I'm going to go. Bye everyone, bye MAKiT.
That's fair. Bye Roblox. Lemon.
And Lemon wanted to explain you something, so
I'm all for it, Lemon. I'm all for an explanation.
Good luck on your explanation, Lemon.
Alright.
Bye everyone.
Give me a second. I need to just go to... Oh, fudge. MAKiT got screwed up. There we go. And there we go. And there we go. Give me a second, because I have some chicken on my stove. Heat it up. Yeah, I'm just heating up some chicken because I'm hungry. I'm finally back. What did I miss? Thought you missed maths. I don't know how much you enjoy maths, but you've kind of joined at the perfect time to not to miss the maths. Well, I mean, there's gonna be more maths. Lemon's about to explain the musical icebergs, which I mean, that's kind of mathematical, I would say. Okay. Okay, alright, my chicken is warming up. It's had my midterm, so I think I've had my share. Fair reason, I would say. I would say that's fair. I would say that's really fair. Okay, so I'm back. Now, let's get back into this. So, what I'm trying to do here is I want to color in the balls so that they will go from red to blue. Let's imagine we have some differential form. I'll describe as pdx plus qdy plus rdz. Okay. I think I'm with you so far. P, Q, and R are functions of x, y, z. Makes sense? So far, I'm with you. If this is gonna work, I will not believe it. Because you need the index, doesn't make sense for it to be the index. Yeah, exactly, then just changing the color of the wrong thing. What if we change, oh, don't divide by 0. What if we change a point? Or even better, instance. That. Let's have some corresponding vector PQR. You see, hold your horses now. The vector of functions. Couldn't help but notice. You have a vector of functions. Let's slow down now. I was with you so far, but now we have a vector of functions. Yeah. Okay. It gives a vector field. Yeah, you see where you lose me. You see, where I think you lose me is that I don't understand how a vector field of functions would work. So hold on. Okay, when you have a vector field of values, right? When you have, I'm thinking of it in a way that's too simplified. It's not generalized enough. That's the problem. The problem there is that I don't explain how a vector field works. Yeah, but can you explain it in a general enough way for me to understand how a vector field of functions would work? Use functions to define the vector field, make it. Yeah, but the thing is, what would that mean to have a vector field of PQR? I can understand PQR as a vector, but not quite as a vector field. Or like an operator on a vector field. I can also understand that. I don't quite get it as a vector field. But once again, that's because, you know, I don't have that generalized kind of idea of what a vector field is. Okay. Okay, so the x component of vector field it assigns at some x value is dependent on p. X component of a vector field it assigns at some x value is dependent on p. But in one way is it dependent on p? Because is the function changing? Like how is it dependent on p? Calc plot 3D. I can if you want. LibreText! Oh, let's LibreText, everyone. Okay, there we go. Calc plot 3D. What do I do now? Unless you want the non-LibreText one. Which I mean I can, but you know, I would prefer the LibreText one for obvious reasons. My beloved. Okay. Add to graph. See vector field and click it. Vector field. Alright. I have a vector field. What now? Wait, hold on. Is it a vector field as in at each point you just have a vector that's equal to p of x, q of y, and r of z? Like you have a... because I just realized that you said vector space, a vector field, not a vector space. That's what confused me. I was thinking for some reason of a vector space. So like when you have a three-dimensional vector space, then at any point you just have a vector which x, y, z. Great, that beautiful drawing in 3 dimensions. Which x, y, z is equal to p of x and then q of y and then r of z. Is that what you mean? I meant vector field. I know you meant the vector field because you said vector field. I just saw vector space for some reason. Okay, then I get you. All right. So let's go back to it. Have some corresponding vector. All right. So it's a vector field PQR then. All right. I'm with you. I'm back with you. I'm sorry for throwing in the background. I'm just really hungry. Okay, so there's just some function. Okay, so there's just like some functions which give you back the xyz over vector. Okay. So we currently have pdx plus qdy plus rdz, and we also have pi qj rk. Okay, what's pi qj and rk? as the basis vector for x, y, and z respectively. Wait, okay, so you're using I, j, and k as basis vectors for x, y, and z. But... Wait, what? I'm lost again. Because the way I understand it is you would need a different vector space to change. Does a vector field also change the basis vectors? So you know how I wrote it as PQR before? Yeah, I remember that. There's so many layers of vectors. There are so many vectors there. There's so many... Too many vectors. Guys, go p00 plus 0q0 plus 00r. That makes sense. Right. So these are the basis vectors. Okay, so is that the I, j, and k then? Is p00 just I? Is p00 equal to I? You know, like... Hang on, then, because otherwise I can't see. P00 is equal to p times the vector 100, which I'm using as an x-axis basis vector represented as I. X basis vector. Wait, hold on. So, whoa. All right. I see. Okay. So it's just the standard basis. All right. Then I'm back with you. So basically, have, jeez. So it's basically like P. Okay, so Pi, Qj, and Rk basically tells you how much in x direction is it going with P, how much in the y direction is going with Q, how much in the z direction is going with R, because all the other ones get multiplied by 0. Because it's a clean basis vector with no... Okay, then I'm back with you again. The chicken is helping. Without the chicken, I wouldn't help. Wouldn't be able to understand. Alright then. And now for the big reveal. The suspense is killing me. Also, I'm eating chicken, major. Okay. Shaft is the tool let's convert this into this. No, because you defined it. I see. Wait, hold on for a second. Hold on. give me a second. What you initially said with the P, Q, and R isn't nabla, is it? Like, it's not nabla, right? PDX plus QDY plus RDZ, that's not nabla. Or is it nabla? It's not. It's not nabla. Okay. How is it different from nabla? Because my problem is that I get how that would be useful if it was nabla. And I want to use that as an anchor point to understand how that would be useful. How is PDX plus QDY plus RDZ different from nabla? PQ and R functions. Hold on. River operators in each corner's house. Yeah. I just don't quite understand how how the sharp would work. I don't get it because I mean, hold on. What is PDX? Maybe that's probably where I'm going wrong. What is PDX? Because I thought I get it, but apparently I don't. Because this function P multiplied by dx, that's all it is. Okay. Neat. So find sign of an integral. However, the problem element is that with an integral, you also have the infinite sum of them, right? That's what I'm struggling with. And the entire bit there is that you take infinite amount, infinitely thin slices. If you just have an infinitely thin slice, then because I'm assuming that's not 0, right? So what is PDX exactly? Because dx is approaching 0, correct? Like, what makes this equation different from 0 plus 0 plus 0? Or rather, because it's multiplied by something that's approaching 0, so it doesn't really matter how big p would be, right? It is a very, very tiny rectangle area. Okay, hold on. Is it approaching 0 or is it not? I think it's about tiny. I mean, but like, the pickle there I'm having is that the way I've learned about dx, right, is through the integral, and the whole bit of the integral was that this is basically multiplying by 0, this is basically multiplying by infinity, but they get cancelled, but it's not undefined because of a limit, and that actually tells us about the function due to that limit. Why does lemon make it 1-1? Because I'm trying to understand what sharp means. That's why. So if you take away the infinity, doesn't the 0 just take over? Because if you have p dx, then isn't that just like a limit as dx approaches 0? Or rather, I guess it would be a limit as x plus h minus x. H approaches 0, but at least that's, as I mentioned, that's the definition. I can give you an example, please do. You know the Riemann sum? I have heard of the Riemann sum. Wait, hold on. Am I thinking of the right sum? I don't know if I'm thinking of the right sum. Riemann sum, give me a second. I have heard of it, I just want to know which sum it is. Oh yeah, okay, this sum, right. Have heard of it, yes. One of the terms of the Riemann sum. So hold on, is dx approaching 0 or is it not? That's confusing. That's what's confusing me. Like, what is dx in this case? Any cool books you recommend? LibraText, that's it. It's not really cool, just I don't, the only time I read books, when for videos like these, I need a source material, so I wouldn't say I have any cool books to recommend. Is a change in x that approaches 0 but does not ever actually reach it, because that would be make the whole area come out as 0 as undefined. Okay, but then what does it... What? I'm really confused again. Like, it's approaching 0. So shouldn't the whole value also approach 0? So for example, you know, in if you have 3 times h limit as h is approaching 0, like that equals 0. So what's different about p times h? Oh, dx, but they're both approaching 0, so that's equivalent. Taking integral under curve usually gives non-zero area. Yeah, but that's only because you have an infinite amount of them. That's why. If you actually took a finite sum of infinitely thin rectangles, you would still get a 0. That's why the integral has to be infinite. As I mentioned, with the integral, you basically have integral f of x dx, and this is the 0, this is the infinity, and they're both like fighting each other. In this case, you have not necessarily, but like, can you give me an example of a finite, of something that doesn't have a 0, that doesn't have an infinity, that when multiplied by 0, multiplied by something that approaches 0, would not give you 0. So we know limit h approaching to 0, something in here that when multiplied by h will not give you 0. Because I just can't imagine what would have to go there for this to not be equal to 0. That's not P for now because some sort of case factor of ds. Yeah, okay. Let's ignore the P. I have two values, 0 and 0.0001. You following? Yes, I am. Distance between them as well as 0. Yes, that is the distance. It's a very thin distance, a bunch of times we don't get 0. Yes, however, if the limit is approaching a 0, then you would need to add up an infinite amount of them. Yeah, but as I mentioned, in this case, what you're basically saying is that we don't have to get a 0 if this is multiplied by x, where x is equal to limit as c is approaching 0, 1 divided by c, basically. Like, this is what you are saying. This will give you a 1, I guess. I wish I had the Rolex, yeah. No, but I mean, you see my problem. I mean, okay, hold on. Because there we go. You see my problem. It's that in this case, this would be true, but you would need another thing that goes off to infinity. Like, as I mentioned, because this is basically the part I'm struggling with. Can you give me an example of what I would need to put in this box here for this to not be equal to 0? Because if I get that, then I feel like I'll understand the p. Actually, I guess we can remove the h because it is a bit confusing. Hold on. H isn't really necessary. Dx. X divided by h, or rather, okay, so right here you used to do x divided by dx, that kind of thing. So inside of the p, we would also have dx. Like p would also be in some way proportional or inversely proportional to dx, like on the inside. But wouldn't then that mean that if you have pi, wouldn't this then be equal to infinity? Because right here, you're no longer multiplying it by dx. Like the thing is, if you define px as equal to x divided by dx, then this would be equal to x, but this would be equal to, wouldn't that be equal to infinity? That's what I'm struggling to understand. Let's ignore the integral stuff for now. But this, I mean, but you can't just leave me at that. You really just tell me that you can have a function which can be both multiplied by something that's approaching 0 and multiplied by a scalar, and in both cases it would give you something, and you're just gonna leave it there without giving me an example of a function. Necessarily involve require integrals to work. Let's just ignore them for now. Okay, fine. Fine. Let's pin the example later. U is equal to x squared, right? I'll be honest, Lemon. My integration is not quite up to speed these days, but yeah, I trust you. Du divided by dx equals 2x. Does that make sense? Yes, it does. That so far makes sense. Hold your trade, don't want to get too lost with this a minute. Lemon, I already got lost like 17 different times. I am going to get lost. It's not a matter of not getting lost, it's a matter of of getting back, honestly. Which you can't treat it as a fraction of some black magic fuckery. You can't treat it. How would you solve for du if du divided by dx is equal to 2x? Well, du is, and it feels like a trick question. Define solve. Would you consider this to be solved? Multiply dx both sides to cancel out the drift. Okay, yeah. So yeah, I'm on board with you so far. Holy fuck, I fixed it. Oh my goodness. Ah, it worked. Okay, I'm ready now. And now that 2x dx is an example of the whole pdx thing. But this will still just equal to 0 if you just take it. Wouldn't it? What am I missing? Wouldn't that just equal 0? Like 2x dx. No. What? You just... Like, the thing is, the problem, the limit is that up to this day, I've considered myself pretty decent at calculus. So you're just kind of completely wrecking my entire calculus world right now. This isn't equal to 0? How? What? How? How is this not equal to 0? Your idea of integral and dx fighting each other is kind of wrong, no offense. No, but I mean, dx is approaching 0. Like, integral is irrelevant in this case. Dx is approaching 0, is it not? Wait, is the dx approaching 0 or is it not? Like, integrals aside, there's just a limit. Being wrong about integrals is one thing, but me being wrong about limits is like a much larger issue in this case. The thing is, very tiny and look like 0 to approaching 0 isn't the same as equaling 0. Hold on. I mean, that's an equal sign. That's an equal sign. That's an equal sign. How do you mean? I mean, how do you mean? Lemon, you're wrecking my entire understanding of calculus right now. Because limit as x approaches 0 of x, like you can multiply it by whatever you want. You can multiply you can multiply x by trying to. I'm sorry. I mean, no, I just don't understand how limit of as x approaches 0 of x could be not equal to 0. Because what you said, very tiny and looking like 0 due to approaching it, isn't the same thing as equaling 0. I don't have no other to put this. That just feels factually incorrect. I don't. And you can multiply x by anything. So, for example, 10,000, right? It wouldn't make a difference. Oh yeah, because I'm multiplying the limit, aren't I? Yeah, if you multiply the limit, that's if Wolfram Alpha understands you. Big if. Is there multiplication, or can I not do it with because I don't want to do convolution on accident? It's because the x isn't just x approaching 0, it's a change in x approaching 0. Okay, so in this case it would be h up, but you see, my problem with that is that the reason why I said approaching 0 is because the actual definition of the x, you are right, is correct, but it is just x plus h minus x. That is the actual definition of the x, which is still 0. That's why I simplified it, because it was the same limit. Hi, paper. Hi. These errors can avoid or ultimately p by dx, right? So you're just gonna leave me hanging? Lemon? Lemon? You just gonna... You're gonna join in, look me dead in the eye, tell me that you can have this, and just refuse to elaborate. Lemon! I am so confused about this. I am so... Okay, my problem with this... I know x equal to 0 when x is 0. Generally feel really bad, but I have no more to explain. I just don't understand how... Because, okay, this is the part I am struggling with. Like, to distill it down, this is exactly the part I am struggling with. The fact that A and B are not equal to 0 and not equal to infinity. Like, that's what I don't understand. I can't imagine a way in which both A and E would have to be not an infinity and not a 0 at the same time. Because it's either right here, this limit squashes it into a 0, or you want to divide by dx in the p, in which case you would get an actual value, but then b would just skyrocket to infinity. And I just don't see a way out. Damn it. I'm gonna be thinking about this now. Oh, this is going line by line. That's even worse. Well, it's not even worse. It's so bad. Shouldn't go line by line. I'm genuinely super fucking sorry because I tried everything I can to explain it. I just don't understand how that could be. I really... I wish I would, but... I just don't understand. Set ID. Yeah, right here, set ID. Is it going line by line as well? That thing is not working. What's your favorite piece of literature, MAKiT? I would say, good. I don't know. I don't think I have one. I'm just trying to imagine a function which would work there. Yeah, and ask if you can explain what is the wagon able to. I am just the most confused. Okay, I should specify. Well, PDX exists not being equal to 0 is fine. It's this I don't get. And then it is basically PDX which is equal to A. So PX dx, because it's a function, so I'm just gonna plug it in. It's a private functions with no stuff. B, where both A and B are not 0 or infinity. I don't understand this. In the meantime, all I can tell you is the following. Going back to our P dx, Q dy, and R dz, and Pi qj rk. Okay. With you so far back again. Isn't walking all of a sudden. It's dumb. Shall we change between into this and flat lets us do the opposite? I mean, I get that. It's just that I don't know what, what we're changing basically. Like the basis vectors with functions, I get that. This is basically a function for each direction. I don't understand the other one. So I know that they're changing. Think of it as a tool that technically lets us replace differentials like dx or dy or dz in their corresponding basis vectors. That's fair, but as I mentioned, Like, I don't know what differential we're switching from. Lemon, I don't know if you sent a video link, but YouTube doesn't allow that actually. YouTube doesn't allow sending video links. Just a fair warning if you tried sending a video link. That size of 24 should be it, I think. No. No, that's wrong. That's all wrong. Perfect. Oh, perfect. Yes. Yes. Oh my goodness. Yes, please. Yes, please. Okay. Okay, we can do maths now. All right. Tensor of beginners and are convectors. Hide the family and that's and whatever explanation Reblex comes up with, combine lighting for self. Lemon, I don't think so. I don't think so. Lemon, I want you to realize that Reblax joined in on stream to explain, specifically to explain musical isomers to me, and I did not understand. And go with 1 right here, and then let's go with a scale. Uh-oh, yeah, I should have seen that coming actually. Divide by 100. There we go, and then they start from 0 to sweet, and then color rump. We have a color rump here, that's nice. There we go, and then as we slowly decrease it to 1, oh, I mean 0.5. First one is 0, fuck, we need to add 1. There we go, and then 101. Shoot. Wait, no, I'm wrong. Oh, how should I do it? Hold on. How should I do it? How should I do it? How should I do it? This. Yup. Starts at 1. Is then going up to 101. I wish I could just telepathically transfer my knowledge and ways of thinking about PX. But you can see why I'm confused, right? Like, the thing is, if dx is defined as the limit of x plus, or as limit as h approaches 0 of x plus h minus x, like this would be equal to 0. You can see where I'm confused, right, with this. Oh, I want to min-max this. I'm an idiot. Right, I want to divide it by 10. And then... Well, this can use the min-max, actually. Let's do 5. There we go. Actually, we could do it backwards. We could start at 0. Actually, we could start at 5. There we are. And 900. Okay. Imagine like this with 100 molecules. 950, because why not? -95, -95, -100. I mean, it's because I divide by 5. Yeah. Okay, there we go. Hey, studios, thanks for modeling and rendering both. You know what? I think I'm gonna go for today. I'll be honest. It's been a long stream already, and it's been a lot of maths. So those two together don't go well. So I think I'm gonna go. I'm really tired. I'll try to get some sleep. And yeah, I guess I'll see you tomorrow. Tomorrow I'll try to finish this video, hopefully. That's hopefully. I don't know if we'll get there. I know we'll get that's only a try. And for now, I suppose that'll be it. Thank you everyone so much for watching. And have a great day. Bye. Oh, but first, before I go, thank you so much for happy birthday, Ramit. Thank you. Oh, I appreciate that. I'm so glad someone remembered.